Chapter 4.
अच्छा, तुम्हाला होस्ट केलाय.
Okay.
मी लीव करते.
Okay. You are able to see the book.
Yes, sir. Yes, sir. Able to see, sir.
So have you gone through the last chapter when we dealt with heat exchangers?
Heat exchangers.
Book 2.
Yes, sir. Yes, sir. Heat exchangers. Yes, sir.
So with this, what you can do is perform a test to determine the overall heat transfer coefficient of heat exchangers in the field. Determine the effectiveness of heat exchangers in the field. Anybody
From this
else is likely to join?
I think we have, only two. I think.
Last
Only
time when Mr. Ajit was there for some time.
Suresh, sir. Only Suresh has joined, sir. Suresh Abhat. Or, I think 2-3 minutes we can wait, sir. I think they will join. Only 9-5.
So we'll start our session. May
Sir.
take time, that's why.
So any question will come, sir, in from this topic in the exam? Heat exchangers.
Yes, it will.
Okay.
Boilers, definitely there will be a
Boiler.
question.
That,
Yeah.
that big question is likely to come, no, sir. That one. Boiler.
Yeah. Heat exchangers also,
Sir.
it is likely. Short questions will be there, I think.
Short question will 10 marks question, sir. 10 marks. Sure.
Heat exchangers are equipment that transfers heat from one medium to another. Shell and tube heat exchangers are used extensively throughout the process and power industry, and as such, a basic understanding of their design, construction, and performance is important to the practicing engineer. The proper design, operation, and maintenance of heat exchangers will make the process energy efficient and minimize energy losses. Now, we have seen various types of heat exchangers, right?
Yes, sir.
And different kinds of flows.
Yes, sir.
So what are the different types of heat exchangers?
Shell and tube
And
shell and tube heat exchangers. And this.
And plate type heat exchangers.
plate type heat exchangers and tube in tube also.
Yeah, tube in tube.
Okay, tube in tube, basically a single tube and another annular tubes are there too. Okay, shell and tube and plate type heat exchangers. Then what type of flows according to
Parallel
flow of the two mediums?
Yes, sir. Parallel flow is there, sir. Counter flow.
And
cross flow.
Cross flow.
So
three different kinds of flows are there, but many times true counter flow or true cross flow may not exist. In shell and tube type of heat exchanger, there are baffles inside the shell, right? So on the medium and the shell side, it is in some place it is a counter clockwise, it is parallel also, or cross current and counter current, like that it goes. Okay, and if there are two passes in the tube side, then again parallel and cross will be there. Now what purpose of the performance test? What is the purpose? Heat exchanger performance can deteriorate with time of design operations and other interference such as fouling, scaling, corrosion, etc. What is the difference between fouling and scaling?
Scaling is formed inside the on the tubes are scaling.
Okay, but because of
Deposition
some
of
deposition of salts
salts.
in the medium,
Yes, sir.
and fouling means what?
Fouling.
Fouling is a physical obstruction. Okay,
The physical obstruction. Yes.
so that particular thing may not be all the time there, but it has come and clogged the tube, say. That is called as a fouling, or it is partially clogging the tube. That is fouling. And corrosion, you know what it is.
Yes, sir.
So it is necessary to assess periodically the heat exchanger performance in order to maintain them at a high efficiency level.
Yes, sir.
This section comprises certain proven techniques of monitoring the performance of heat exchangers, coolers, and condensers from observed operating data of the equipment. The objective of performance assessment is to determine the heat exchanger duty, overall heat transfer coefficient, heat exchanger effectiveness, process or utility side pressure drop. Any deviation from design will indicate occurrence of fouling. Okay, delta P, when we are seeing pressure drop across the different mediums, if it is deviating or the pressure drop is increasing pressure drop means what? When the pressure drop will increase,
Pressure drop.
if there is a
when the-
constriction in the path,
yeah, obstruction in
the path.
yes.
So that obstruction, if it remains, that particular area will not be available. That heat transfer area will not be available for transferring heat, right? So we have to remove that obstruction, and this obstruction can be cleaned. So say tube side it is there, so tube side we can clean easily. Okay, with long brush and rod and brush, we can clean the heat exchanger. Now, and scaling is a cumulative phenomena. It's not that suddenly it will deposit on the tube. Over a period of time, gradually the scale will build up. Now, what is scale? Scale, what are the properties? Is it good for heat exchanger, bad for heat exchanger? What is it?
It's bad for heat exchangers, sir.
And why?
Yes.
Because the heat transfer will not take place, sir. It will obstruct the heat transfer.
That means the scaling, that conductivity of the scale which is formed on the tube is less, right?
Yes.
That is
Makes
why
sense.
the heat transfer, heat exchange will not take place. So it is necessary to remove the scale as well. So
Yes, sir.
first thing is we should avoid the scale forming material in the medium. So in case of water, how
Scaling.
we can control that is there, that is a possibility is there that we can control the quality of water itself so
Yes,
that
sir.
the scale formation will not take or we remove all the salts from the water.
Yes, sir. Water quality.
So
Okay, yes.
scale formation will not take place. And talking about water, because in most of the cases you will find the mediums as water.
Water.
In case of boilers, it is definitely there. Boiler itself is a heat exchanger, isn't it?
Yes, sir. Yes.
There are a number of heat exchangers in the boiler. And in the boilers, why it is important is because with high pressure, the scale or the salts will segregate and deposit on the tubes. So the water quality, maintaining the water quality is most essential in case of boilers or high pressure and high temperature. Both are there. But other heat exchanger also, the performance of the heat exchanger, if it gradually decreases, say take the case of a condenser. When the steam turbine is there and the exhaust is to be condensed and there is fouling on the tubes or the performance of the condenser reduces, that means what will happen? It will not condense at that temperature or pressure. So pressure will start increasing. Back pressure in the condenser will start increasing.
Yes.
So if your aim is that a particular temperature has to be reached, you will not be able to attain that objective. And heat transfer, in case of condenser, you don't have a choice to add some more thing immediately. So you will have to take a shutdown, do the cleaning, and put it in service again. It's a long process, basically. And if you know of power plants, if a power plant of say 500 megawatt, 660 megawatt, it has to be shut down. That means you lose the generation for those many days, right?
Yes, sir.
So that is one of the examples for maintaining the heat exchanger effectiveness or maintaining the heat exchanger for better efficiency or higher efficiency levels.
Sir, how to reduce the fouling, sir?
Fouling, of course, you can have the filters in the inlet itself.
The filters and things.
Yeah.
Now, what are the material obstructing, sir? Actually, fouling causes fouling. What are the
Cause of
components?
you are not use the proper water. Say if there are no filters, you are taking the water from the lake, cooling water from the lake.
Okay.
Then there are various chances that some foreign particles will come in, foreign material will come in, like leaves or even the silt and other things will come along with the water.
Yeah, okay, sir. Achievable.
And there is a chance that if the diameter of this material is slightly higher than the tube diameter, then it will choke the tube.
Mhm.
Of course, in the design, they normally take care of putting additional number of tubes in case any tube gets fouled or any tube gets punctured. There's a possibility of puncturing the tube also.
Yes, sir. Yes, sir.
So if it gets punctured, then you have to plug the tube because removal of the tube and say attending to the leak is not possible. So you have to plug the tube. So once you plug the tube, then that much surface area is not available for you,
Sir.
right?
So water contaminants only will cause fouling, sir. Watering.
Yeah, water or any some such thing, or
Okay.
anything in the circuit.
Circuit. Okay, sir.
Suppose any small part or something wears out and comes in the flow, that also can cause fouling. But in the large condensers, there are now systems where we can clear the fouling by back flushing. Online, you
Sure.
can do that. Part of the condenser or part of the tubes. There are filters in the inlet side. This is especially there for when you are taking, say, seawater or water from the lake directly for condenser cooling. Then such things can happen. So they provide the filters which will not allow large particles to go in. And those filters, if they get choked, we can clean those filters by backwashing online. That means that small portion, I say 25% of the condenser portion for a short while will have a reverse flow. And whatever fouling has taken place on the filter, that will be cleaned. The filter will be cleaned and taken back in service. It is a question of few minutes only.
Okay, sir.
Okay.
Yes, sir.
So these are important things. And performance assessment to determine the heat exchanger duty, overall heat transfer coefficient, heat exchanger effectiveness, process utility side pressure drop. Any deviation from design will indicate occurrence of fouling. Now, performance terms and definitions. What is the overall heat transfer coefficient, U?
You.
We have seen in the previous chapter also. The overall heat transfer coefficient, U, represents how easily the heat can move. A smaller value of U indicates the difficulty in in the transfer of heat and vice versa. That means U value should be higher and higher. Heat exchanger performance is normally evaluated by the overall heat transfer coefficient that is defined by the equation Q is equal to U into A into LMTD, where Q is equal to heat transferred in kilocalories per hour. A is heat transfer surface area in square meters. LMTD is the log mean temperature difference in degrees centigrade. And U is the overall heat transfer coefficient, which is in kilocalories per hour per square meter per degree centigrade. Okay.
Yes, sir.
So you have to be careful about the units. I am repeating again and again, because in the earlier chapter you have seen the Q in kilojoules. Here it is given in kilocalories. So unit consistency should be there for that particular equation. When the hot and cold stream flows and inlet temperatures are constant, the heat transfer coefficient may be evaluated using the above formula. Heat exchanger effectiveness, that is, effectiveness is indicated as epsilon. Actual heat transfer rate in kilocalories per hour upon maximum possible heat transfer rate in kilocalories per hour. That will give you the effectiveness of heat exchanger. That is equal to Q, that is actual heat transfer rate, divided by Q max. Now, what is Q max? Q max is equal to C min into delta T max. What is this now? C is the heat capacity in kilocalories per hour per degree centigrade. That is equal to mass flow rate in kg per hour into specific heat capacity of fluid in kilocalories per kg per degree centigrade. That means mass flow into specific heat is the heat capacity of a particular fluid. Okay, and what
We are
is
not able to see the screen, sir. Screen, the book is not visible, sir.
Yeah,
screen is not,
yeah, it is visible to me, sir.
Yeah,
I think,
visible
Acha.
to me also.
please
Oh,
check your setting, I think.
okay, sorry.
is it okay?
Yeah, yeah.
Yes, sir. No, I'm
Yeah,
able to see, sir. No.
yeah. Mr. Ajit has joined. I think last time we could not introduce ourselves. For a minute, Mr. Ajit, can you switch on your camera, video camera, and tell about yourself?
Yeah. Good morning.
Good morning.
Good morning. My name is Ajit Warakar, basically mechanical engineering graduate. I'm freelance auditor training consultant. I'm into auditing profession, lead auditor of ISO 9001, 14001, 45001, 50001. I'm associated with certification bodies, TV Nord, as their auditor and trainer for various management system. Basically, freelance consultant and over 28 years of experience in industry, auditing, training, and consulting.
Okay, your video was not on.
Just a minute. Okay. I hope I'm visible.
Yeah, okay.
Okay.
Hi. So, you know about me. I am associated with Prerna since its foundation. I am a founder member, and I have experience in large thermal power plants, about 40 years of experience. I am a certified energy auditor as well. Okay, let's go ahead. So, whatever questions you have, you can put on the WhatsApp. Okay. So Q upon Q max is equal to Q upon C min into delta T max. Now C min is, you have seen heat capacity. So heat capacity on the cold side and heat capacity on hot side. Out of two heat capacities, whatever is the minimum, that is taken here for calculating maximum possible heat transfer rate. And delta T max is the maximum temperature difference from terminal steam temperatures. That means hottest or hot inlet minus cold inlet or cold inlet. The most commonly used methods for heat transfer analysis are LMTD-F method and the effectiveness NTU method. This section gives an overview of LMTD-F method. F is the correction factor. Now the LMTD is logarithmic mean temperature difference and used to determine the temperature driving force for heat transfer in heat exchangers. So as we have seen that heat transfer takes place because of what? What is the potential? When you find a possibility or potential of heat transfer, what is the driving force? Is the temperature difference
Temperature difference.
between the two fluids, right? So higher the temperature difference, higher will be the heat transfer rate. Now, the LMTD is logarithmic mean temperature difference and used to determine the temperature driving force for heat transfer in heat exchangers. It is determined by the relationship of the fluid temperature differences at the terminals of the heat exchanger. LMTD correction factor. If the flow is true counter current, the LMTD calculated is used directly in the basic heat transfer equation. If the flow is not true counter current, that is more tube passes than shell passes, LMTD must be corrected and also to account for cross flow. So in shell and tube type heat exchangers, this F factor will come in picture. In multi-pass shell and tube heat exchangers, the flow pattern is a mixture of counter current and co-current flow, as the two streams flow through the exchanger in the same direction on the some passes and in the opposite direction on others. For this reason, the mean temperature difference is not equal to the logarithmic mean. However, it is convenient to retain the LMTD by introducing a correction factor F, which is appropriately termed as LMTD correction factor. Okay, why that correction is required? Fouling factor. One of the important heat exchanger parameters related to surface conditions is termed as the fouling factor. The fouling factors to be used in the design of heat exchangers are normally specified by the client based on his experience of running his plant or process to simulate dirt accumulation on the heat transfer surfaces. But if these are not restricted to proper levels, they can totally negate any benefit generated by skillful design. That means if you do not maintain these parameters, the fouling factor represents the theoretical resistance to heat flow due to build-up of layer of dirt or other fouling substances on the tube surfaces of the heat exchanger, but they are often overstated by the end user in an attempt to minimize the frequency of cleaning. In reality, they can, if badly chosen, lead to increased cleaning frequency. The fouling factor increases with increased fouling and causes a drop in heat exchanger effectiveness. Common types of fouling are chemical, biological, deposition, and corrosion fouling. So the scaling or whatever chemical deposition, etc., is also a form of fouling. Okay. Fouling means basically what it is doing is causing a restriction to flow. Restriction to flow. If the deposition is there and it keeps on building up over a period of time, then the tube diameter will be affected, isn't it? Tube diameter will be affected, it will reduce and cause more pressure drop across the tube. So industrial heat exchangers, the most common types of commercially available heat exchangers are the shell and tube heat exchangers. Nomenclature. A typical heat exchanger is shown in the figure 4.1 with nomenclature. Now you can see this part is the shell, and the tubes are passing through these. These are supported by the tube sheets at two ends. This is called as a tube sheet, and the tubes are passing through this till the other end. Now here you can see there is a partition at the inlet. The hot fluid in is coming from this end, entering the tubes here. There may be number of tubes over here, and the fluid passes through the tubes, comes to the other end. There is no partition in this case, so it flows in the other direction and goes out from this and goes out from here. Hot fluid out. So there are baffles in between inside the shell. Okay, the tubes are passing through those baffles. Or those baffles actually act as supporting for the tubes as well. If this length is very large, then they need the support also in between. Otherwise, due to flow of the two mediums on the shell side as well as tube side, it can cause vibrations of the tubes and if they are not properly supported, there could be tube failures. So this is hot fluid passing through the tubes and coming out, and cold fluid is coming from on the shell side, on this side. It is because of the baffles, it is going like this also. So when it is passing over these tubes, it is a cross flow. And when it is coming like this, in this case, in the other pass, one pass, it is a parallel flow, right? Hot fluid and cold fluid in the same direction. Whereas in this case, it is counter flow. Is this clear? This half of the tubes is counter flow, and this of the half of the tubes, it is parallel flow. In this case, here, in this section, it is cross flow. So all three of them are there. And that is where we need the correction for the LMTD. Is this clear to you all?
Yes, sir.
Okay, now whenever there is a fouling takes place, how will you come to know? If there is fouling, which parameter will immediately indicate fouling?
Heat transfer will be less, sir.
Heat transfer is the effect. What is the immediate question? Heat transfer is coming down, you will know definitely. But pressure drop, pressure drop
That's right.
across inlet and outlet. The pressure drop, design pressure drops, you may know. And if this goes beyond certain limit, then only the heat transfer will be affected. But within that, within the certain margin, you will come to know the pressure drop immediately.
Yes.
Duration of the pressure drop.
Pressure drops.
Okay. Now, why I'm saying tube side cleaning is easier, because you can open this this side of the man. There are manhole covers given here, so that person can enter. Or handholds will be there for a smaller heat exchanger, and you can see the tubes from here, access the tubes, and clean the tubes with brush and the long rods. Whereas on the shell side, even if you enter, you cannot reach in between tubes, because there will be a formation of the tubes, say in the triangular form, or some formation will be there. There are a number of tubes in the heat exchanger. So you will not be able to access any of the tubes rather. Only outer section you may be able to access. Inside tubes you won't be able to access. So cleaning becomes difficult. So while choosing this type of which fluid will flow on which side, you have to choose the one which is less fouling or clean fluid, or having less of salts or deposition you can avoid. That should be on the shell side. Of course, there may be some restrictions for it, for choosing this thing. You may not be always able to do that. But this is the case. And that is why tube cleaning is easier. And in many cases, online tube cleaning systems are used. Online means there are sponge balls which are introduced on the tube side, and they are slightly oversized, rather the oversize of the tube. and their surface is hardened, little bit hardened. So when the those balls are introduced in the inside the water box here, they pass through the tube because it is being a sponge ball, it squeezes through, but it passes through the tube and scrubs the tube basically. So it doesn't allow the silt to build up over there or scale to build up over there. And when it comes out from the other side, the balls are collected here, water flows out, and the balls are reintroduced in the inlet side. If you have worked in any of the power process industry, you may be knowing these things. Has any one of you worked in the process industry?
No,
Anybody?
sir.
Okay. Now, heat duty of heat exchanger can be calculated either on the hot side fluid or cold side fluid as given below. So, heat duty for hot fluid is W. W is the basically flow of the fluid, flow rate into Cp hot, that is the heat capacity into delta T, Thi minus Tho. Similarly, heat duty for cold fluid is equal to flow rate into specific heat of cold fluid into delta T of cold fluid. Now we are assuming that whatever heat is given by one fluid is absorbed by the second fluid, right?
Yes, sir.
If the operating heat duty is less than the heat design heat duty, it may be due to heat losses, fouling in the tubes, reduced flow rate, hot or cold, etc. Hence, for simple performance monitoring of exchangers, heat duty may be considered as a factor of performance irrespective of other parameters. A deviation in heat duty may not be a conclusive indicator of fouling due to variation in process condition. Okay, so the flow rate may change, and if the flow rate changes, then the delta T also changes. So that is not the process indication of fouling. However, the overall heat transfer coefficient offers itself a reliable indicator of fouling. Hence, the performance assessment of the heat exchanger is carried out by determination of overall heat transfer coefficient in the field. So that is why overall heat transfer coefficient is quite important to find out any deviation from the design values. Now, what is the methodology of heat exchanger performance assessment? Procedure for determination of overall heat transfer coefficient U. This is fairly rigorous method of monitoring the heat exchanger performance by calculating the overall heat transfer coefficient periodically. Technical records are to be maintained for all the exchangers so that problems associated with reduced efficiency and heat transfer can be identified easily. The record should basically contain historical heat transfer coefficient data versus time on date of observation. A plot of heat transfer coefficient versus time permits rational planning of an exchanger cleaning program. So you will know when to clean the heat exchangers. Now, in a continuous process industry, you cannot afford to stop the process and do this cleaning. So, in many cases, there are standby heat exchangers provided. So, you take one heat exchanger when you are to take out for cleaning. to take the other standby heat exchanger in service and then do the cleaning of the other. The heat transfer coefficient is calculated by the equation U is equal to Q divided by A into LMTD. It is the same equation which we have seen. Q is equal to U into A into LMTD. So U, if you have to find out, you will know you have to find out Q divided by A into LMTD. Now where Q is the heat duty, A is the heat transfer area of the exchanger, and LMTD is the temperature driving force. The step-by-step procedure for determination of overall heat transfer coefficient is described below. Step A, what is to be done? This table is given, what monitoring and reading of steady state parameters of the heat exchanger under evaluation as are tabulated as below. You must note that steady state parameters, because if there is a changing scenario and at that time you take the reading, that means you are changing the flow, and at the same time you are taking the reading, it will not give you the proper picture. You will have to wait till the process stabilizes. Okay. So hot fluid flow, W in kgs per hour, cold fluid flow, hot fluid temperature, cold fluid temperature, hot fluid pressure and cold fluid pressure in bar gauge, inlet, outlet. So this you have to note down.
Oh.
Yeah. Yes. Yes. Any questions?
Bar G means, sir? G.
Bar gauge.
Gauge. Okay.
Okay, because
Okay.
absolute and gauge value, that is the difference.
Gauge pressure. Okay.
Okay. Step B, with the monitored test data, the physical properties of the stream can be tabulated as required for the evaluation of thermal data. So when you know hot temperature and pressure, you'll know hot fluid density, kg per cubic meter, inlet and outlet. Cold fluid density, inlet and outlet. Because density changes with temperature. So from the given tables, you can find out these values. Then hot fluid viscosity, cold fluid viscosity, and hot fluid thermal conductivity and cold fluid thermal conductivity. Hot fluid specificity and cold fluid specificity. So these parameters you have to note down. Density and viscosity can be determined by analysis of the samples taken from the mass from the flow stream at the recorded temperature in the plant laboratory. Thermal conductivity and specific heat capacity, if not determined from the samples, can be collected from the handbooks. So handbooks in these values, conductivity, thermal conductivity, and so specific heat you can get. Now, calculate the thermal parameters of heat exchanger and compare with the design data. Okay. So, heat duty Q, what is the test data? Means whatever parameters you have taken, from those parameters, you compare it with the design data. So, hot fluid, delta P, cold fluid, delta P, temperature range, hot fluid and cold fluid, capacity ratio R, effectiveness S. So these are dimensionless parameters. We'll come to these parameters too. Corrected LMTD or MTD, mean temperature difference, log mean temperature difference or MTD. So when can we you say that mean temperature difference? When can you use?
When the LMTD comes 0, sir.
When LMTD comes 0?
When both sides temperature, this side, that side are both are equal, then it comes 0, sir.
Temperature difference of both the sides.
Both the sides.
So that will be only in case of true counter flow.
That will be the
Yeah. So heat transfer coefficient in kilowatt per square meter per degree Kelvin or per degree centigrade. Now step D. Now you have to find out heat duty. The following formula are used for calculation of thermal parameters. These parameters you have to note down. So how to calculate? Heat duty Q is equal to QS plus QL. What is that QS? S is for sensitive heat and L is for latent heat.
latent heat.
Okay.
Yes, sir.
So for sensible heat, QS is equal to flow into Cp, that is the specific heat of hot fluid, multiplied by delta T of hot fluid, divided by 3600 in kilowatts. Or QS is equal to, from cold side you can find out. For latent heat, QL is equal to mass flow rate into lambda H. Lambda H is the latent heat of condensation of a hot condensing vapor. So if there is a condensation, then only this factor will come into picture. Otherwise, this factor is not going to come in picture. Clear?
Yes, sir.
Units, you have to be very careful. Now, hot fluid pressure drop, delta pH is P inlet minus P outlet. Cold fluid delta P, P inlet minus P outlet. Temperature range hot fluid delta TH is equal to THI minus THO, and temperature range cold fluid is TCO minus TCI. Now calculate LMTD. So these are common things. Now if it is a counter flow heat exchanger, then delta T1 and delta T2. So that means hot fluid side inlet is termed as delta, difference is termed as delta T in, delta T1, and hot fluid outlet side is termed as delta T2. So temperature distribution for a counter flow heat exchanger will be like this. So this is delta T1, this is delta T2. For parallel flow, this is the delta T1 and delta T2 is this. So now LMTD counter flow is equal to delta T HI minus CO, HI minus CO. That is T1, delta T1, and minus HO, THO minus TCI, THO minus TCI upon natural log of THI minus TCO divided by THO minus TCI. Similarly, for co-current flow, THI minus TCI, because they are parallel, so on the same side, minus THO minus TCO divided by in natural log of THI minus TCI upon THO minus TCO. The LMTD correction factor F. The LMTD correction factor is a function of temperature effectiveness and the number of tube and shell passes, and is correlated as a function of two dimensionless temperature ratios. Let R and P be the two-dimensionless parameters used to calculate LMTD correction factor defined by the equation below. So R is equal to TA minus TB divided
that
by
means,
TB minus TA.
sir, we have to calculate two LMTDs, sir, counter current and
No. Whatever case may be given, if it is given as a counter current, you will have to calculate for counter current. They have given the example for both of them. How to-
so, in one example which we have seen, there are both the flows, no, sir, counter flow and parallel flow also.
Where?
In one example we have seen, sir, in the actually shell and tube heat exchanger, which we have explained. The counter
Yeah.
flow is there and parallel flow also is there.
Yeah. So in that case, you will have to use that particular for
Both of them.
that much surface area. That will be affected by the surface area. Now in this case, R is the dimensionless factor. TA is the inlet temperature of shell side fluid. TB is the outlet temperature of shell side fluid. TA is the inlet, small TA is the inlet temperature of tube side fluid, and small TB is outlet temperature of tube side fluid. From that, you are taking the R and P factors. R factor is shell side temperature difference, and this is tube side temperature difference. On this TB minus TA, so this is the reverse of that, inverse of R. And no, not inverse. This is TA, that is the inlet of hot side and inlet of cold side. The difference in this. Similarly, this also, this is TB minus TA, that is the outlet of the small cold fluid and inlet of cold fluid, or tube side fluid rather.
No, shell side fluid means hot side, sir. Shell side fluid.
Not
Tube
necessarily. Not necessarily always. It depends.
How do we know, sir, which is shell side, which is tube side?
So that will be given to you, no?
In some figure.
And hot side and shell side, you know how the shell and tube side. See, this is the shell side inlet.
Yes, sir.
This is tube side inlet, tube side outlet. This is shell side outlet.
Acha, side is tube side. Say. Okay, sir.
So in chapter, in book 4, this is an open book test. But you must remember where this formula is available. Otherwise, we will waste time in searching the formula itself. Because remembering is a bit difficult, no doubt about it. But you can refer to the formula. So alpha is equal to 1 minus Rp divided by 1 minus P raised to 1 upon N. What is that N? And S is equal to, capital S is equal to alpha minus 1, alpha minus R. So from all these factors, you have to finally find out F factor or correction factor for LMTD. That is equal to R under root of R square plus N 1 and log natural log of 1 minus S upon 1 minus RS. Now, how it is being divided, how it has been found out is not a question we are dealing with here. We have to use the formula. So that's how we are going to keep track of correction factor for LMTD. S is equal to P upon N minus 1 into P. F is equal to so much. For R equal to 1, that is what we have calculating. Now, N is the number of shell side passes. Capital S and alpha is equal to parameters used to calculate LMTD correction factor defined by the equations given above. Corrected LMTD is equal to F into LMTD, or overall heat transfer coefficient is equal to U into Q upon U is equal to Q upon A into corrected LMTD. N is the number of shell side passes. Okay. Heat exchanger effectiveness. Now, how we calculate the effectiveness? The heat recovery capability of a heat exchanger is characterized by means of an index referred as the heat exchanger effectiveness. Is a measure of thermal performance. Calculate the heat exchanger effectiveness. Calculating heat exchanger effectiveness helps engineers to predict how a given heat exchanger will perform a new job. To predict the stream outlet temperatures without a trial and error solution that would otherwise be necessary. Definition: the heat exchanger effectiveness is defined for a given heat exchanger of any flow arrangement as the ratio of the actual amount of heat transferred to the maximum possible amount of heat that could be transferred between the two streams with an infinite area. This you note down. What is infinite area? We have seen in the earlier thing, when you say that infinite area is available to you, that means both the outlet temperatures of outlet temperatures will become equal. Okay. Hot outlet and cold outlet, if they are same, that means you have achieved full effectiveness of the thing. Definition: heat exchanger effectiveness, that is the maximum amount of heat that can be transferred. Okay. The latter is the rate of heat transfer that could occur in a counterflow heat exchanger having infinite heat transfer area. In such an exchanger, one of the fluid streams will gain or lose heat until its outlet temperature equals the inlet temperature of the other stream. In counter flow, it will be this case. In the parallel flow, it will be the other way. The fluid that experiences this maximum temperature change is the one having the smaller value of heat capacity. C is equal to maximum mass flow rate into specific heat capacity of the at constant pressure, as can be seen from the energy balance equation for two streams. Thus, if the hot fluid has the lower value of C, we will have THO equal to TCI, and Qmax is equal to WCPH into delta T or THI minus TCI. That is equal to C min into delta THI minus TCI. So this is found out if the hot fluid has the lower value of C, that is mass flow rate into specific heat capacity, then you use this. On the other hand, if the cold fluid has the lower value of C, then TCO is equal to THI. And Q max is equal to, you can take this as the C min into THI TCI. This you will have to remember. You have to understand what is the heat capacity, first thing. Heat capacity is mass flow rate into specific heat. So whichever is the minimum, depending on that minimum C value, you choose the equation which can be used. So thus, in either case, Q max is equal to C min into THI minus TCI. THI minus TCI is the maximum temperature difference, right? Is this clear? THI minus TCI is the maximum temperature difference in that particular heat exchanger, whether it is counter flow, cross flow, or parallel flow. This is depending only on the inlet temperatures. Your heat exchanger has not come into picture for calculating Q max. Is this clear? First, let me know. Yes, sir. Is the concept clear, basically? THI minus TCI. Okay. What is heat capacity minimum? You understood? Heat capacity is flow rate into CP. Flow rate into CP of means hot
Cold
fluid or cold fluid, and whichever
Cold.
is minimum, that has to be taken.
Hmm.
And THI and TCI, any heat exchanger value you take here. Okay. THI and TCI. This is the maximum temperature difference. Similarly, THI and TCI. This is the maximum temperature difference, right?
Yes.
So, for any type of configuration of the heat exchanger, this will be the maximum temperature difference. THI minus TCI, or THI here minus TCI. So this is almost equal, rather. This is the same as this one. So heat capacity you have understood, and minimum heat capacity has to be used for and maximum temperature difference has to be used. This will give you Q max. That is the maximum heat transfer rate is C minimum into delta T max. And effectiveness is actual Q divided by this Q max. Have we seen this? Effectiveness is given by effectiveness Q upon Q max, that is equal to Q upon C min into delta T max. Heat capacity ratio R is equal to C min upon C max. That is WCPH upon WCPC. hot and cold. It should be emphasized that term effectiveness may not be confused with efficiency. The use of term efficiency is generally restricted to the efficiency of conversion of energy from A to in A to energy form B, or a comparison of actual system performance to the ideal system performance under comparable operating conditions from energy point of view. Since we deal here with a component heat exchanger and there is no conversion of different forms of energy in a heat exchanger, although the conversion between heat flow and enthalpy change is present, the term effectiveness is used to designate the efficiency of a heat exchanger. The consequence of the first law of thermodynamics is the energy balance, and hence the definition of heat exchanger explicitly uses the first law of thermodynamics. Okay. Energy balance. First law of thermodynamics is the energy balance. And that is why heat exchanger is using first law of thermodynamics. In the book 2 chapter, we had a question. One of the question was this: whether it uses first law of thermodynamics, second law of thermodynamics, or none. So the answer we have got here: exchanger explicitly uses first law of thermodynamics. Right, Mr. Ambedkar?
Yes.
Yes, sir, because this thermodynamics law is basically energy can be neither created nor destroyed. It can convert from one point to another. So this is what maybe it is
Yeah,
due
that's
to
why
that.
he's saying that it is the energy balance. It's from one form to other, it can go, but anyway, here it is not going from one form to other, but balance is maintained. Energy balance is maintained. So whatever hot side you are giving out, cold side is taking it.
Yes, yes, correct.
For air-to-air heat exchangers, when the two streams have the same mass flow, such as the case of makeup air system, the expression of the effectiveness referred to as the efficiency can be further simplified to efficiency is equal to TCO minus TCI upon THI minus TCI. THI minus TCI is the maximum delta T, and TCO minus TCI is the cold side taken. Heat capacity ratio is equal to TCO minus TCI upon THI minus THO. If the effectiveness heat capacity ratio was given as a R, no? If the effectiveness of the heat exchanger is 0.5, this does not mean that the heat exchanger is only 50% efficient in its transfer of thermal energy. By conversion of energy, any energy that is lost on one side must be gained on the other side. So in that way, we could say that them as 100% efficient, but the effectiveness is actually just a measure of ability of the heat exchanger to exchange temperatures, not the energy, but exchanger temperatures. In a perfect counterflow heat exchanger, if a perfect counterflow heat exchanger should be able to get the two fluids to swap temperatures, assuming the same fluid and mass flow rate, if a 50%, 50 degrees centigrade, A is equal to 50 degrees air and B is equal to 90 degrees air going through a perfect heat exchanger, then we should get a 90 degrees C air and B is equal to 50 degrees C air out of it. So 50 and 90, 90 and 50. So all these temperatures are swapped. Okay. that is 50% effective would give you 70% air out from both the streams. So what does this mean? When it is 100% heat exchanger, perfect heat exchanger means 100%. So you are getting 50 air inlet temperature to be as the 90 degrees air inlet. So A will be assuming A side stream will go to 90 degrees and B side stream will come down to 50 degrees air out of it. That is 100%. So when it is 50% effective, would mean 70 degrees centigrade air out from both the streams. That means 50, this temperature difference. How much is the temperature difference?
40
50 and
degrees.
40 degrees. So when you say that 50% effective, make it as a 40, half of 40 is 20. So 50 plus 20 is 70, or 90 minus 20 is 70. So 70 air out will be from both the stream. If the effectiveness is 50%. Is that okay? Got it? Hello?
Where is the formula for this, sir? 90 minus 20. Only 40 is the LMT.
Formula is not given, but we have to assume that. Say when it is 100%, that is what he is saying. When it is 50% effective, would give you 70 degrees centigrade air out from both the streams. So whatever difference was there, 50 to 90 was the difference, okay?
Yes, sir.
So there, when it is 100% effective, you can exchange 40 degrees temperature.
Yes, sir.
So when it is 50% effective, of the 40, you will exchange only 20 degrees.
Okay.
So are you getting it now?
Yes, sir. Yes, sir. 50%, 20 degrees.
Yeah.
Then 70 degrees is the
Outlet of both the
air
flows.
out. Air out from both the streams. That's all. 90 minus 70, 20. Okay.
Yeah.
Very simple. This.
So examples. A shell and tube heat exchanger of the following configuration is considered being used for oil cooler with the oil at the shell side and cooling water at the tube side. Tube side, what is given? 460 numbers, 25.4 mm OD and 2.11 mm thick into 7211 mm long. So from this, you will be able to find out how much area, surface area is available for heat exchange. Okay. Pitch is 31.75 mm at 30 degrees and triangular, 2 pass. This is your tube side is 2 pass, means whatever shell and tube heat exchanger we have seen in the other picture, that is a 2 pass on the tube side. Shell side 787 mm ID, baffle space 787 mm and 1 pass. That means comes and goes, that's all. The monitored parameters are as follows. Hot fluid flow is given, cold fluid flow is given, inlet and outlet flow will remain the same, right? Hot fluid temperature and cold fluid temperature, inlet outlet given. Hot fluid pressure is also given. Cold fluid pressure on both sides is given. Hot fluid specific heat capacity, CP, is given, and cold fluid specific heat is given. So calculation of thermal data. Heat transfer area, they have calculated as 264.55 square meters. How you will calculate that?
Heat transfer area 460 numbers into 220. Pi d square. What do you outlier? Heat transfer area. Surface area we have to calculate, sir.
Surface area. So you have to calculate the periphery.
Periphery means outside 250. Pi d, sir. Pi d.
Ideal,
Into
na,
length.
sir? Yes, ideal.
Ideal. 25.4 into 2.1.
2.1 is not, that is the thickness.
Thickness, yes.
That you don't consider.
3.14 into 7.211.
Into number of tubes.
The number of tubes 460.
Hmm.
So if we calculate, it comes and answer same thing, force.
So 264.55 square meters. So millimeters has to be converted into meters. Now heat duty. Heat duty is equal to Q. QS plus QL. So hot fluid. Now this is oil. There is no L coming into picture, I think.
Cold fluid is water, sir.
Cold fluid is water.
Cold
Hot
fluid
fluid
is
is
water.
oil. Hot fluid is
Hot
oil.
fluid. Yes, sir. Yes. Yeah,
So hot fluid flow is given.
QS plus Q1 is QS.
And flow into Cp into delta T. So divided by 3600 will give you in kilowatts.
That's how hot fluid Q is equal to 71. The formula is there.
Here. This is mCpdt. You remember this formula. M is for mass flow.
Yes, sir.
Cp is the specific heat.
2.84.
And delta T. Delta T is for the hot fluid, whatever is delta T. And since this Cp is given in kilojoules, Cp is given in kilojoules per kg degree centigrade.
Kilojoules, correct.
If you have to convert into kilowatts, you have to divide by 3600. Will give you kilowatts. Cold fluid Q is equal to this much. Now you have to consider minimum of the two. Hot fluid pressure drop is you can calculate directly. Cold fluid pressure drop you can calculate directly. Temperature range you can calculate. Now LMTD.
By 3600, how they have put, sir? 3600, sir.
Which one? 3600 is, see, kilojoules per second.
Yes, sir. Well, that is kilojoules per
Convert
second.
into kilowatts. Kilojoule per second is basically
What?
Kilojoules. So if you have to convert it into
kWs.
kW, so you have to kilowatts 3600 से divide करना पड़ेगा. 60 into 6 per second. So per second से per hour. So that is, you have to convert that way. Now LMTD. This is a shell and tube type, and there are two passes on this side, tube side. So THR, TCO, TCI, TCO. For counter flow, this is LMTD. LMTD correction factor for account for cross flow also. Now RP, you have to calculate. R is 1.83. So for R not equal to 1, alpha we are calculating like this. N is the number of passes. S is equal to this formula. So all these formulas you will have to refer. So F comes out to be 0.977. Corrected LMTD is F into LMTD 0.977 into 85.9. That is equal to 83.9 degrees centigrade. Overall heat transfer coefficient U is equal to Q upon A into corrected LMTD. So Q is equal to 244.77.4 divided by, this is the area, 264.55 into corrected LMTD. That comes out to be 1.104 kilowatt per square meter per degree centigrade. So you map all this test data and design data. So design data will be given here, and so from here you know what is heat duty. Actual duty difference will be practically negligible, as these duty differences could be because of specific heat capacity deviation with the temperature. Also, there could be some heat loss due to radiation from the shell side. When you compare this, now hot side pressure drop delta pH 1.3 test data and 1.34 is the design data. So this could be because of the flow pressure drop. Also, the pressure drop in the shell side of the hot fluid is reported normal, only slightly less than the design figure. This is attributed with the increased average bulk temperature of the hot side due to decreased performance of the exchange. That means the delta P is less. It indicates that the condensation temperature of that vaporization temperature has increased, or the pressure has increased. So that's why the delta P has reduced. Are you getting me? Say water boils at 100 degrees at atmospheric pressure. But if the pressure is increased, what happens? The boiling point goes up. The boiling point goes up means, in this case, if you say that this temperature here corresponding to the pressure in that hot side, if that is higher, the pressure is higher, or say shell side, whatever pressure of the outlet you can see, we are seeing the delta P across the heat exchanger. So THO or PHO, if it is higher, then PHI is the same, PHO is higher. So this delta P will reduce, and that reduction could be because of the heat exchanger effectiveness. One of the reasons for that. This is attributed with the increased average bulk temperature of the hot side due to decreased performance of the heat exchanger. Temperature range, as seen from the data, deviation in the temperature range could be due to the increased fouling in the tubes, cold stream, since higher pressure drop is noticed. Cold fluid side, pressure drop is slightly higher, and temperature range is also lower. Okay. So since the pressure drop is more, there could be a fouling, and that is why the range has reduced on the cold side. So that is how this comes into help for analyzing the performance of the heat exchanger. Why we are not seeing the fouling on this side, hot fluid side? Because this pressure drop is there. Pressure drop is
Two only.
less than whatever is the design. So if it is less, what could be the possible reasons? One is the effectiveness has reduced. It could be because of the less flow on the cold fluid side. That is also possible. If the flow on the cold fluid side reduces, the temperature will not be come down to that extent. But here the temperature range, also there is a difference in of 2 degrees. Here also 1.5 degrees is there. Corrected LMTD or MTD. So design data is 82.2, whereas here it is 83.8. Heat transfer coefficient 1.104, and here design data is 1.178. So heat transfer coefficient has reduced. So overall heat exchange has reduced.
But LMTD is more, no, sir. LMTD.
LMTD is more in this case. Corrected LMTD is more.
That means
But
more
as
transfer.
a overall thing, see, LMTD less and more, that is one of the indications that heat transfer could be higher, but there are some other parameters which are causing the less heat transfer. And finally, what you are seeing, heat transfer coefficient U, it will affect U only. If U is better, then you are achieving whatever you desire. That means here the U is less. So as per design, it should have been 1.178, whereas it has reduced. That indicates that because what are the other parameters for finding out heat flow rate? You are using UA into corrected LMTD, right?
Yes, sir.
So area remains the same. A is same.
Yes.
U has reduced because of
Hot fluid.
other factors, whatever factors are there. LMTD, though LMTD is more, your U has reduced. So Q also.
LMTD is in the denominator, no, sir.
Yeah. For U, it is in denominator.
For you. If LMTD is less, U will be more.
LMTD is less.
If LMTD, U will be more, no, sir.
Yeah. So temperature range, as seen from the data, deviation in the temperature ranges could be due to the increased fouling in the tubes, cold streams, since the higher pressure drop is noticed. Heat transfer coefficient. Estimated value has decreased due to increased fouling that has resulted in minimized active area of heat transfer. Physical properties, if available from the data or lab analysis, can be used for verification with the design data sheet as a cross-check towards design considerations. In the above example, 4.6a, determine the effectiveness of heat exchanger and heat capacity ratio. To determine effectiveness of heat exchanger. So hot fluid, C oil is equal to, this is the heat capacity, okay? Heat capacity is flow rate into, that is M into Cp. Since this is in kilojoules, we are converting to kilowatts. So divided by 3600. Cold fluid, seawater, this is the capacity. Now C minimum is hot fluid side is the minimum 569.24 and C max is 1024.83. Now Q is equal to 24477.4, which we have seen in the example. And delta T max is hot side inlet minus cold side inlet. That is 119.5. So effectiveness of heat exchanger is actual Q. Q is given divided by Q max. And Q max is equal to C min into delta T max. So that's how you are getting effectiveness of the heat exchanger as 0.36. And heat capacity ratio R is C min by C max is equal to 0.55. This is clear. Basically, the formula you are adding the values to the formula. A plate heat exchanger with total heat transfer area of 41 square meter is used to exchange heat between a hot effluent stream and cooling water stream. The monitored parameters are given below. Hot fluid flow, hot fluid temperature, and cold fluid temperature. Calculate LMTD and overall heat transfer coefficient, assuming LMTD correction factor of 0.9. For plate heat exchanger, specific heat capacity of hot stream is 4.187 kilojoules per kg degree centigrade. So solution is hot load is Q is equal to flow mCp dt. Okay. Flow is 85,200 kg per hour into 4.187 is the specific heat in kilojoules, kilojoules per kg degree centigrade per degree centigrade into delta T 77 minus 54 divided by 3600, that gives you 2279 kilowatts. LMTD counter flow will be 77 minus 57. That means T hot in minus TC out minus 54 minus 49. That is TCO, THO minus TCI divided by natural log of 77 minus 57 upon 54 minus 49. That gives you 10.8 degrees centigrade. Correction factor is 0.9. So corrected LMTD will be 10.8 multiplied by 0.9 is 9.72. So overall heat transfer coefficient U is equal to Q upon A into corrected LMTD. So Q is 2279 divided by 41 is the area of in square meters into 9.72 is equal to 5.718 kilowatts per square meter per degree centigrade. So this you will have to practice. A double pipe heat exchanger, we have some time. Double pipe heat exchanger is used to cool a hot stream from 177 degrees centigrade to 121 degrees centigrade by heating a cold stream from 49 degrees centigrade to 77 degrees centigrade. The hot stream will flow in the inner pipe in a counter flow arrangement to the cold stream in the outer pipe. The heat transfer surface area of 18.5 square meters will transfer the heat load of 1025.85 kilowatts. Determine the overall heat transfer coefficient U. So LMTD counterflow, use the equation that comes to 85.2. Overall heat transfer coefficient U is equal to Q upon A into LMTD. So this is the heat load divided. This is the heat load divided by area multiplied by LMTD. Comes out to be 0.651 kilowatts per square meter per degree centigrade. Now surface condenser. A shell and tube exchanger of the following configuration considered being used for condensing turbine exhaust stream with cooling water at the tube side. Tube side, this is 20,648 numbers, number of tubes, 25.4 mm OD and 1.22 mm thick and 18,300 mm long. That is almost 18 meters long. Pitch 31.75 mm, 60 degrees triangular. One pass. So tube side is only one pass. Monitored parameters are as below. Hot fluid flow, cold fluid flow, hot fluid temperature, cold fluid temperature, and hot fluid pressure and cold fluid pressure. So bar gauge, here it is only millibar. What does that indicate?
That means 42, 52.2 divided by milli, by 1000.
By 1000. Yeah.
But outlet is not given, sir. Outlet is 48.3. Inlet in this much temperature. I think
That is also millibar.
that's also millibar, sir.
Yeah, yeah.
Okay.
It can't increase the pressure. No? So calculation of thermal data, area is given. Area, as we have calculated in the earlier case,
Yes, sir.
these are number of tubes, pi dl. What to do? So area is coming out to be 30,151 square meters. Duty is.
Sir, what is the use of giving the pitch, sir? Is it just for the information? Pitch they have given.
Pitch is basically required for certain calculations on the
Good.
while designing you need all these things.
Okay.
Given
It is
the
just
pitch
for information.
for information here, they have not used that information for our example.
Calculation.
So you can see how that will be. You can see, I'll show you this picture. Can you see this notebook? Is it visible to you? This picture.
Yes, sir. Yes. It is a triangular picture. Yeah, pitch, I understood, sir. It is
Pitch.
yeah,
Pitch is the distance between the
distance between the
center line of the two tubes.
tube. Yes, sir. Yes.
So they will be distributed all over that surface. So that pitch actually affects the flow of the steam over the tubes. So duty of hot fluid is flow multiplied by latent heat of vaporization. That we should find out from the tables, steam tables,
Sure.
right?
That they will not give, sir. We have to find out. 2210.
They may give also. In some cases, they may give. But in book 4, probably they may expect you to find out.
Okay.
Just check whether this steam tables or any such book is allowed to be taken in. But every time you must be careful about the units they are using. Now, why this 3600 has come? Because you are calculating the mass flow rate or measuring the mass flow rate in kg per hour. So you have to convert it into kg per second.
Yes, sir.
Because kilojoules per second will give you kilowatt. Right?
Yes, sir. Yes.
So that's why that 3600 has come in the earlier thing also, because of kg per hour. You are converted into kg per second.
But in previous problem, this latent heat of vaporization is not used, no, sir, at all. Hot
No,
fluid is
not
good.
latent heat, but basically conversion of kilojoules to kilowatts.
That's okay, sir. 3600 is okay, understood, sir. This
But then
2210 hot fluid Q is equal to mass into latent heat of vaporization.
hot fluid, because it is a condenser. In
Acha.
condenser, what you do? What type of heat exchange takes place? The temperature remains almost the same.
Okay. So
See,
earlier, how we have
there is
said.
no data here.
Yes.
This is only the outlet is given.
Mhm.
Since it is a condenser, ideally, this will be the same. This will be at the same temperature. Should be.
No, sir.
But why the data is not given? Because for flow of that fluid, this should be at a higher pressure, slightly at a higher pressure. 52.3 millibar and 48 point means just how much? Only 4 millibar
Mm.
is the difference in pressure. So if this is high at higher pressure, definitely this temperature is going to be higher than this, slightly higher than this. Latent heat, you know what it is, saturation temperature.
Latent.
So when the saturation has reached, the entire thing will remain at the same temperature, right?
Yes, sir.
So ideally, for condensing, this temperature also should be equal to 34.9. But this cannot happen because it is not a bath sort of thing. The steam has to flow over the tube. So for flowing of the any fluid, there has to be a pressure difference. Just as the transfer of heat from one to other, there has to be a potential
Pressure.
temperature difference. For flow, there should be a pressure difference. If the pressure remains the same, there will not be any flow. Right?
Yes, sir.
So that is why they have not given any data here. So cold fluid mass flow, this will give you the temperature difference, mass flow rate into CPC into temperature difference. So this is cold fluid Q is equal to so many kilowatts, and hot fluid is this one. So C min and C max, you know, this
Yes.
min.
So that 2210 is as per steam table, latent heat of evaporation
Yes, yes. At that pressure,
at that millibar pressure.
millibar pressure, yeah.
Okay.
Hot fluid pressure drop is 52.3 minus 48.3, that is 4 millibar. Cold fluid pressure drop is 4 minus 3.6, that is 0.4 bar. Temperature range, hot fluid, temperature range is equal to THI minus THO, no data. Because THI you don't know. Cold fluid temperature range 9 degrees centigrade. So LMTD calculated considering condensing part only. Hot fluid temperature at inlet and outlet remain the same. Okay. That is why 34.9 degrees centigrade is considered. LMTD counterflow is calculated from this 11.8. Correction for factor to account for cross flow, F is equal to 1, that is given. So corrected LMTD is equal to F into LMTD is equal to 1 into 11.8. Heat transfer coefficient, overall heat transfer coefficient U is equal to Q upon A into T max or delta T.
Sir, F is equal to 1 where they have given, sir? F is equal to 1 means.
They might have given or it is considered as 1. You can write that.
Okay. Yeah, it's not.
This is one pass.
One pass. F is pass, sir?
Tube side only one pass is there.
Yes, sir.
So that is why that one factor has come. There is no counter current that in that case. Comparison of calculated data with design data given here. So now for analysis, what do you do? Heat duty, actual duty difference will be practically negligible. 588,430 and 576,990. So percentage wise, if you see, will be very less. Would be because of the specific heat capacity deviation from the temperature. Also, there could be some heat loss due to radiation from the hot shell side. So this will be, there will be a difference on heat duty on both the sides.
Sir,
See,
588,430, where it is given, sir? 588,430.
5 design data. Now they have not given, but they have later on they have given this in the example. But for your question, they may give it the design data. So basically, they may ask you to compare. You may not be calculating the entire thing. They will give you this type of table and ask you to analyze. So heat duty, actual duty difference will be practically negligible as the duty differences could be because of specific heat capacity deviation from the with the temperature. Also, there could be some heat loss due to radiation from hot shell side. This will always be the case. That is why hot side heat and cold side heat, that those values will not match. Exactly. Because there is some loss from here. Shell side,
Radiation.
because it is on the outer periphery. So pressure drop, the condensing side operating pressure raised to the back pressure caused by non-condensable. This has resulted in increased pressure drop across the stream side. Four millibar, 3.7 to 4. So the pressure drop has increased here. So increase in pressure drop is, as we have seen in the earlier case also, it could be because of the higher back pressure. That means the temperature that is 34.9 degrees, if it has not reached, it is not the design value, then if the temperature is higher, that means the pressure is also higher. Temperature range with reference to cooling water side, there is no difference in range. This is 9 degrees. However, the terminal temperature difference has increased, indicating lack of proper heat transfer. This is 11.8 and 8.9. So this has increased. Heat transfer coefficient. Heat transfer coefficient has decreased due to increased amount of non-condensable with the steam. Non-condensable means there is say oxygen. Oxygen in water will be released at that pressure, and that if that is not removed from the shell side, it will accumulate in the shell, causing the pressure to increase. Right. So in this type of systems, you will see that steam ejectors or vacuum pumps are used to maintain the vacuum or to remove these non-condensable gases from the shell side. Troubleshooting. Operations may be checked for tightness of circuit and ensure proper venting of the system. The vacuum source might be verified for proper functioning. That means if there is a, see this, these values which are there, 4 millibar or 3.7 millibar, they are lower than the gauge pressure, lower than atmospheric pressure. Okay, these are absolute pressures. So, since it is under vacuum, the condenser is under vacuum, there is a possibility of air leak from the atmosphere. If there is any possibility of leak, if the system is not tight, air could leak into the condenser. And if air leaks into the condenser, that means it is increasing the back pressure. And that is causing this heat transfer coefficient, that reduction in heat transfer coefficient. Okay. Flow rate of the hot and cold water streams flowing through a heat exchanger are 12 and 30 kg per minute respectively. Hot and cold water stream inlet temperature are 72 and 27 respectively. The exit temperature of hot stream is required to be 52 degrees centigrade. The specific heat of water is 4.179 kilojoules per kg per degree centigrade. The overall heat transfer coefficient is 800 watts per square meter per degree centigrade. Neglecting the effect of fouling, calculate the heat transfer area for parallel flow and counterflow. So rate of heat transfer, mCp dt. So flow rate is given. Now per minute, you have to convert into per hour. This is 12 into 30 kg per minute. So 12 by 60 will be per second.
Per second into 4.179, that is CP.
Hmm.
Delta T is 72
72
minus
minus 52.
72 hot and cold water stream. Inlet temperatures. 72. That's the inlet temperature. 72 minus 52.
So that cold water
1000,
exit temperature,
1000 now it has come, sir. 1000.
there seems to be some mistake here. This is instead of kg per cubic
Minute.
meter per minute, it could be cubic meter per minute. If it
So,
is
sir,
cubic
they have calculated in the watt actually, watt. That's why they have multiplied by 1000.
yes, right. Watt.
Watt, sir. Acha, kilowatt.
Not
Watt.
in kilowatts.
Yeah,
So if it
they have
will be
converted
kilowatt, then this
kilojoules.
1000 is not required.
Okay, sir. Rate of heat transfer. Cold water exit temperature.
Cold water exit temperature is 27, that is the inlet plus whatever heat it has gained. And out of that, that temperature comes out to be 8 degrees. This is the
How this one, sir? 27 plus 167 versus that is MCP delta T again.
this is on the cold water side. This is the rate of heat transfer. So rate of heat transfer means from this medium as well as that medium, right? This divided by
They have
specific.
already used temperature. So they have already used the temperatures, no, sir. Hot and cold water steam in the temperature and outer temperatures also.
No, other side they are not given. 27 is the given temperature of cold water side.
Cold water.
And
So,
exit temperature of hot stream is required to be 52. So for that, how much water? Heat transfer area for this, you have to calculate.
area.
So first we'll have to calculate what is the temperature, exit temperature.
Yes.
And terminal temperature differences now you can find out. 52, 35, 72, 27 for counter flow heat exchanger. Parallel flow heat exchanger and counter flow. It is given. So LMTD you have found out 28.76. Overall heat transfer coefficient is given. Heat transfer area required is the amount of heat transfer divided by this U, and this is LMTD. So that will give you the area. Equation remains the same. Q is equal to UA delta or LMTD, corrected LMTD.
Yes.
Now, terminal temperature difference for counter flow heat exchangers is given in this. So LMTD goes to 30.6. So area is 0.684. So for parallel flow, definitely area required is more than counter flow. So you can go through this. Write the overall heat transfer coefficient U as a function of sensible heat QS and latent heat QL. Will you be able to do that? Because QS and QL will be affecting the Q total. In a shell and tube heat exchanger engaged in heat transfer between fouling fluid and the clear fluid, the fouling fluid should be put on shell side or tube side. I spoke in the beginning itself.
cell side, sir. Fouling food should be on the cell side, no?
It will be on the tube side because it is easier to clean the tubes
Okay.
rather than on the shell side, the tubes.
Okay.
Because fouling fluid, if it is there, you are seeing the pitch. If it fouls in between, how will you clean it?
Okay. Understood.
Explain the terms heat duty and capacity ratio. You have to refer these things now. Capacity ratio R we have seen. Where is it? Capacity ratio R is equal to C min upon C max. And C min is heat duty. C min C max. That is flow rate into Cp. What is meant by fouling? Fouling is restriction either by physical contamination. They have given biological. Biological in the sense, if you are using seawater, in the seawater, these shells and mussels, these are the living organisms. They come and get attached to the tubes inside and they grow there in the tubes. They are very hard to remove, some these type of shells. So that is why chlorination is used in seawater cooling system, so that these organisms do not grow in the tubes. Explain why the term effectiveness rather than efficiency is used in performance assessment of heat exchanger. Efficiency is used in case of energy, whereas this is not exactly the energy use. It is the transfer of temperature. So what temperature can be transferred to other side. Effectiveness, that you can read the example given. Explain the sketch how to determine the LMTD of a counterflow heat exchanger. Explain with sketch. You can draw that. LMTD means THI, TCO, that you will have to find out, show that, and how LMTD is calculated. In a heat exchanger, the hot steam enters at 70 and leaves at 55. On the other side, cold stream enters at 30 and leaves at 55. Find out LMTD of the heat exchanger if it is counterflow type. So only the formula has to be used and you will calculate. In a multi-pass shell and tube heat exchanger, what is the need for correction factor while estimating LMTD? Multi-pass, since it is a multi-pass, on the tube side, it is a combination of counterflow and parallel flow. That is why that correction factor is necessary. What is the significance of overall heat transfer coefficient? What can you say? What does it indicate, overall heat transfer coefficient? See, overall heat transfer coefficient less means what?
So transfer will be less, sir.
Yeah.
That depends the
Particular,
heat.
In a particular configuration, of course, yes.
Yeah.
So write the unit of overall heat transfer coefficient. What is the unit?
Watts per meter square, K, sir. Watts per
Watt
meter
per-
square.
Okay. Or if it has to be in kilocalories?
Kilocalories. Kilocalorie per meter square per K.
Okay. No, these are long questions. You practice yourself. We'll stop here.
Okay.
11.
Yes, sir.
Okay.
Yes, sir. Yes. We can stop.
Yeah. In case of any doubts, you can put the questions on the group.
So we'll get one question from this chapter now, sir. Heat transfer in the exam.
Yeah, possibly, yes.
Heat exchangers.
Short questions also could be there. And of course, the objective type, there could be questions in this. Okay?
Okay, sir. Thank you.
Yes, sir. Thank you, sir.
Yeah. We'll stop then. Hello, Gandhi sir.
Morning. Good morning. Yeah.
Morning.
So I have joined. You can make me host. First, stop the recording.
Yeah. But I will have to leave the meeting. Or
Okay, I will stop it. Don't worry. I will stop the recording.
yeah.
So I have joined. You make me the host now.
Just a minute.
Participants वर तुम्ही मला click करा. On participants.
Yeah.
Yeah.
Okay.
Yeah.
Participants are only 2 or 3 participants are there. Yes.
I have seen that there are only 3 participants. Hope no issue.
Yeah.
Okay, stop.
Anything you want to give feedback? Or you can personally give that.
Yes, sir.
Yeah, sure.
No, yes, sir. It was a good.
So this is actually book number 3, na sir? Book 3.
Yes, this is book number 3.
Book 3.
Chapter is number 10.
Number 10.
Yeah, this is the ECBC.
ECBC. Actually, I have cleared this chapter, sir. This paper has been cleared by me, sir.
Okay, but you can still, you know,
We have to attend.
yeah, no harm in listening again.
Yes, sir. Yes, sir. So, sir, right now also you are doing this auditing, sir. I mean, company
yes.
auditing.
Hope you are able to see the book.
Yes, sir. You can start.
All are there.
Yes, sir. Yes, sir.
Mr. Ambedkar,
Yes, sir. Yes, I am there, sir.
Mr. Sridhar Deshpande, and
Yes,
Ajit.
sir. Yes,
Okay,
sir.
good. So,
Yes,
very
sir.
good morning.
Let's start. Good morning.
So,
Good
we
morning.
are starting with the second lecture of the day. Today's lecture is on Energy Conservation Building Code, which is very commonly, popularly referred to as ECBC. Okay. Actually speaking, this uh, uh, we have just covered a little bit in the first session, energy scenario, where we had just touched upon ECBC, what is ECBC, then how it has developed over the years. But let us start from the basics to understand what is included in ECBC. As I mentioned last time also and today also, I like to repeat the energy consumption everywhere in the world, as also in the country, in India, is nearly 35-40%, maybe 40%, and it's going up, especially with the style, our style of operations, lifestyle, also the commercial buildings coming up, and also the air conditioning requirement going up, as well as the lighting, because now no more we want to, live in a less illuminated area. So the illumination levels are also going up. As a result, with air conditioning loads going up everywhere, with the tropical countries, even the temperatures are going up. So the need for air conditioning is definitely going up, and illumination level going up. So the load on the uh, electrical system is increasing very fast, and so also the energy consumption, the electricity consumption. So the ECBC is concerned about the electrical consumption, how to reduce electrical consumption in the building. Now there are two parts in this EC, in buildings and energy consumption. One is before the building is constructed. Second is when building is under construction, and the third is when the building is constructed and people start using it. Before it is constructed, so the materials which are required for the building construction, like cement, steel, bricks, and all other materials. You all know that all of them, especially cement and steel, they require a lot of energy for manufacture of cement, steel, etc. So this energy that is consumed during the manufacture of the components of energy of the buildings is the imbibed energy. It is called as the imbibed energy. Okay. Then during the construction stage, also there is a lot of energy that is consumed, especially the concrete preparation, then the all your operations, the illumination level, then you require some compressors and electrical supply everywhere. So of course that is not much. It is so that we are not so much worried about that. Now these two are before the building is ready. What the energy conservation building code is concerned about is the usage of building and the energy consumption that is used for various utility systems, and about your our operating the AC, lighting, etc., etc. So energy conservation during the operation of the building or usage of the building, this is what is covered in ECBC. Okay, so I hope that is clear to you that we are not going to talk about the imbibed energy or energy used in construction. That of course also needs to be concerned, but that is an area which is not covered in ECBC. That is covered somewhere else. What this chapter covers is during the usage of the building. All right, please respond so that okay. Is that clear?
Yes, 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 sir.
Okay. No, I do try to get a feedback, so that just want to check that I am audible to you, and we are on the right frequency. Okay. So what we are going to cover in this chapter is the definition of the building. Of course, not we are not going to go very deep into that. Energy conservation building code. What is it? ECBC. What are the ECBC guidelines for the building envelope? Now, what is building envelope? That we will try to see. What are the ECBC guidelines for heating, ventilation, and air conditioning, which is, of course, a utility system? Okay. You all know that heating, ventilation, and air conditioning, HVAC, they go together. So we are studying this together. Then ECBC guidelines for the service hot water, especially the commercial buildings or like hotels, hospitals, etc. They require a lot of hot water. for the patients, for the occupants of the rooms, etc. Then we have got water pumping system, which is essential for every building. So water is consumed in lifting the water and also circulating. Then we have ECBC guidelines for lighting, which is of course a very major source of energy consumption these days. Then in some buildings, in most of the buildings now, especially in our country, we find that the electrical supply is not very stable. So many people use UPS, or what is called as a uninterruptible power supply. I think many of our residences also we do keep it because we are not very sure. It's not 100%. Reliability has increased quite a lot in the last few years. But even then, a momentary, say 5 seconds, 10 second, break can disturb our activities. And in case of the industries, if the power supply disturbs, then there could be a problem in the process. Metals can get solidified, try to get etc. So, they sometimes they use in under triple power supply. Then most of the commercial buildings, residential buildings also nowadays, they have escalators, elevators, which require again usage is quite a lot. So we use energy over there. Then modern buildings, especially the large buildings where the energy consumption is very large, there is a practice of deploying building energy management system. Okay, actually, many of these buildings they do have building management system. So this building energy management is also included in it, and then it becomes building energy management system. And then, of course, like many other products which we have seen also in the first chapter, there is labeling of building that with a star rating of building. So what it is, what is the basis that we'll try to show. So these are all the things that we are going to see. So let's go very quickly to the. I will not again repeat what is given in the blue colored column. I will start with this. Okay, but first of all, I want to remove from your mind that buildings mean it has energy engineers how they are involved so much in it. So let me say that all energy conservation efforts have started by energy engineers in the buildings, any type of building. Actually, it is the Energy Conservation Building Code of 2001. It had a clause saying that Bureau of Government of India and Bureau of Energy Efficiency should come up with a code for reducing the energy consumption in the building. So it starts from there. So the basis is, is Energy Conservation Act of 2001. So there is a mention of that. Now that has been taken as a basis, and for the first time, Bureau of Energy Efficiency was given the task to write down the codes. So they had a lot of consultations, and they come up with a code which was issued in the year 2007. So therefore, for the first time, there was a code for controlling energy consumption in the building, improving the energy efficiency in the building. So what are the measures, etc. And because it was issued in 2007, now it is called as a ECBC 2007. When actually it was issued, nobody said Energy Conservation Building Code 2007. Yes. Yes, Mr. Satyanarayana. Okay, I'll continue. I think there's some. So I will go ahead.
Yes,
So
sir.
uh, Energy Conservation Building Code 2007, what this which was issued, initially is termed as 2007 because subsequently it has undergone revision. That's why it is called 2007. Okay. So basically, we are going to talk first about the original ECBC, that is ECBC 2000 now. Okay. So this is one. Second thing is that, as I mentioned, energy engineers have started it. So they have come up with many suggestions, many proposals, and architects were and civil engineers were supposed to, take action on that. as usual, architects are very, not very enthusiastic about, they were not enthusiastic about taking various measures. So they had to be also told. So both the energy conservation building code has to be now learned by both energy engineers as well as the architects and civil engineers, because both together they only can reduce the energy consumption. Only energy engineers or only architects or civil engineers, they cannot reduce uh, the energy consumption. Now, how architects will reduce energy consumption? Energy engineers, we know that we are operating various systems, so we can reduce it. We have studied all that, along, always we are studying that. But architects have to design the buildings. Architects have to design the utility system in such a manner that during the operation of the building, during the usage of the building, the energy consumption gets reduced to the minimum. So it is actually the role of architects in effort to reduce energy consumption is very, very great. Actually, it is they who are supposed to give us the buildings and the utility system that requires minimum of energy consumption, and various activities that will be later on taken up in the use of the building. So architects and engineers, energy engineers, both are involved in it. Also, of course, along with that, there is a support required from electrical engineers, because to save electrical energy, there are many provisions in the CCBC on electrical system and electrical consumption. Then there are mechanical engineering inputs are required, because there are pumping system and also HVAC and other system which also require electricity. Okay, so that's why the input of mechanical engineers is also required. So this is what it is. So the a building actually imbibes all these disciplines, and that's why it is very interesting. Okay, so let's now try to see how which are the areas of energy consumption and how it can be reduced. You all know that buildings, of course, there is a ventilation, there is an illumination in the building, which will be operated depending on the various types of building. So the energy consumption in the buildings, it depends on various factors. One is the climate conditions. That means if it is cloudy, we require more light. If it is cold, we require heating. If it is hot, we require cooling. So all these require energy. The type of building, whether it's a residential building or a commercial building or a hospital or hotel. Yeah, that also decides the energy consumption, plus the number of working of hours, because some are maybe 24 hours, some maybe only periodic, and the time of the year. These are all they decide the energy consumption in the building. Okay, as I mentioned, energy consumption in the building is increasing fast because of the air conditioning and the illumination, of course, requirements, which are going up very steadily. Okay, so all these things we will have to study. So we have to study the electrical loads, we have to study electrical consumption, we have to see the lighting loads, lighting consumption, air conditioning loads, air conditioning uh, you know, electrical consumption for air conditioning. So these are to be studied as a part of the study of energy consumption in a building. Okay, so this is in general a little bit about the energy consumption in the building. Now although there is a word, it is energy consumption in the building. We don't have to get panicky. It is very simple, because we are all living in the building for many years. We are going to the schools, we are going to colleges, we are going to hotels, hospitals. So we know how is the use of energy. Okay, and as energy engineers, we can apply our mind. Subsequently, how to reduce the consumption, energy consumption, how to improve energy efficiency. So it is not at all difficult, but one has to study all these things. That's why we are going to study this. Okay. Now, so let's come to this now. As I mentioned, there is the definition of the building is the first thing that we want to learn. Now, building is, is an, no, no. which is required for carrying out certain activities. Residential, it's a house. For schools, it is a school building. Then it is college building, hospital, hotels, etc. Everything is called, any building which is a civil structure, okay, which is enclosed, it has got doors, windows, roof, etc., walls, etc. It's a building, okay. But all buildings are not covered. So whenever we refer to a building, it is not that any building, because there are crores of buildings in the world. So we are not talking about all those things. The ECBC is only concerned about certain types of building which are defined as building in the Energy Conservation Building Code and Energy Conservation Building Act. Now, in Energy Conservation Amendment, which has been done in 2010, okay, so there are certain definitions mentioned in that one, in Energy Conservation Act 2010 amendment, of course, and that has reduced certain that had introduced certain conditions. Initially to this 2007, when it was introduced, it was voluntary. Okay, it was not compulsory for any type of building. Then they said that after a certain period of time, once we are used to it, we will make one by one, building sector. It will make it mandatory. So that is how the the buildings, or not all buildings, were covered in it. In the original Act 2001, and the ECBC that was issued in 2007, they mentioned that the limit of uh, a building which has got a load of more than 500 kilowatt, and a contract demand of 600 kVA. Okay, and plus an air conditioned area, but they were specified, and it's a controlled air conditioning that will be considered. Only such building will be considered. Okay, but later on, in the Energy Conservation Amendment Act of 2010, these limits were modified, because initially only a few buildings were getting covered, and their objective of reducing the energy consumption in the buildings was not getting fulfilled for the government. So government made a change later on in 2010 Amendment Act, saying that any building having connected lot of 100 kilowatt, uh, uh, you know, and any building which has got a contract amount of 120 kVA, kilowatt volt amperes, they will be covered. They will be considered. They will be termed as building, and such building will be only covered. So that has increased the compass, coverage of various types of building, and fairly all large energy consuming buildings are being covered now. Okay. So this is the definition of the building. Now let's come to ECBC. Now, the first thing that we said, it depends on the climate zone. So any step that we want to take for energy consumption, it depend on the climate zone, because all buildings are designed to suit certain climate zone. Okay, you all know that there are five climate zones in the country. One is the composite, buildings. One is the hot and dry. The third is the warm and humid. Fourth is the moderate, and fifth is the cold. Of course, air conditioning, people know about that. In air conditioning, we need to study that. But also in the ECBC, because we are dealing with certain provisions which are based on the climate, that is persisting. Now you can see there is a map over here. The one figure, the parts of the country which is shown in red is the hot and dry. Parts of the country where it is warm and humid, like these are shown in dark yellow. Okay, composite buildings, composite environment is shown in light yellow. Then blue is very cold, and temperate means moderate that is also. But that area is, there is only one area. Okay, most of the buildings are either hot and dry, but large part is warm and humid and composite. Okay, so this is, of course, air conditioning people will design we don't have to worry about it. Okay, but we must know. Okay. Now, as I mentioned, there are only buildings which have load more than 100 kilowatt or contract demand of 100 kVA. They are only covered in this, but also not covered in this or excluded from this is buildings which do not use electricity at all. For example, certain warehouses, they may not be using any electricity or fossil fuel. Of course, fossil fuel used in buildings is only in certain cases. Of course, in house we use, but hotels and you know hospitals, they use fossil fuels for heating. But there are buildings like warehouses which don't use, okay, or some godowns, so they are not covered in this. Secondly, equipment and portions of the building that primarily used for manufacturing. So in the initial stage, manufacturing activity, buildings which undertook manufacturing were also not covered. I did mention that only commercial buildings were covered in the initial stage in ACBC 2000, 2007. And five types of buildings were office building, then you had government buildings, you have got private buildings, you have got hotels, and the fifth type of building. Okay. So only few types were there. Of course, later on, various types of buildings have been added as the time progressed, and now many types of buildings are now covered. Okay. Now there are again in the initial stage they had mentioned that there are two approaches. One is the compliance approach. That means they will specify certain limits of energy consumption, so maximum limits of energy consumption, and the architects have to design the buildings and ensure that the consumption in those areas are lower than what is specified in the energy conservation building code. Energy conservation building code, as we will see later on, is a very exhaustive document. It specified the limits of energy consumption for various areas, various activities, so that we will try to see. So one is the compliance approach, and where it's a prescriptive method, means we are suggesting that in a particular area we should use the roof insulation, we should use we should use certain materials which have got certain characteristics, so that energy consumption ultimately gets reduced. Okay, so this is prescriptive method, and there is of course uh, you know there is another method which is called the whole building performance method, where in prescriptive method for each of the let's say if it is wall, or if it is roof, if it is glass, if it is doors, windows, they are specifying the limits for both heat entering in it, or heat going out of the building, and also the light coming in or going out of the building. So there are limits specified for both. Whereas in the whole building performance method, it is the total energy consumption with which this method is concerned, and they only specify only the limit, consisting of all the energy consumption irrespective of which is the area. So these are the two methods which are in practice: perspective method and also the whole building performance method. Of course. Initially it was all voluntary, and later on they started making it mandatory one by one for each types of building. That we will see also as we go along. Okay. So as we mentioned, in the perspective method, there are codes specify, through the ECBC code is a very elaborate document. So one has to go through that, and each chapter is concerned about the energy consumption and limits for a particular part, say walls or roofs or etc. Okay, so and the whole building performance is of course the overall energy consumption in the building. Okay, so this is one, and now before we go to this, we have to also understand that the building consists of an envelope. Okay, so the shelter. So in other what we can call it shelter. That means it has got a roof, it has got a wall, it has got flooring, it has got doors, windows. So building envelope covers the structure with doors, windows, etc. But the functions of you, you know both doors, windows may be different. There are some limits for them. Energy consumption for doors, limits for light coming in or going out, or heat gain, heat from the atmosphere coming in, or heat from within going out, or cold temperature also is included in that, right? So this is what is a prescriptive method and the whole building method. Now, basically what we want to see as the process of architectural design. Okay, we are not concerned about much about the structural design, but mostly it is the architectural design which is to be considered for reducing the energy consumption. So the basic steps that will be involved in the design of the buildings will be design a building with all energy efficiency methods. Okay, right from the starting. So very important. Architects have to take care of that. Then that once they are imbibed, then you have to construct, and then you have to demonstrate that the building complies with those uh, measures which are specified in the code. Okay, design is one part, but proving that every building has been designed and constructed as per the provisions of the ECBC. That is the next step. And third is, of course, use of some tools, external tools like the software, which can be used for controlling the temperatures. And of course, they are also using simulation software to reduce the energy consumption, in the buildings, so that just models have been divided. There are many softwares available which can do they can do a lot of iteration, a lot of changes in the design, and ensure that energy consumption is reduced. So the software is very extensively used by the architects these days to ensure that buildings are energy efficient building, okay, or less energy consuming building. So this is the present status of energy consumption in the building. Okay, now let us try to see one by one what are the guidelines for energy consumption in the different components of the building. So, have you understood what we have said so far?
Yes, sir.
Okay.
Yes, sir.
Actually, it's a very common sense, for us. We are all conversant with the building. Okay. But we have to connect it with energy consumption, and, because there are limits specified, we have to see what is specified. Okay. So we go to the building envelope. Now, building envelope, as we mentioned, consists of walls, consists of windows, consists of roof. Then there may be skylight, doors, openings, and so on in the building. So in the building envelope, uh, you know, if it is air conditioned building, we have to ensure that air conditioning buildings are separate. If there are different temperatures allowed for different areas, we have to also ensure that they are properly segregated, properly insulated. Okay. Then so that especially ECBC covers air conditioned buildings where air conditioning and not the normal types of building. Okay, so that's why uh, we have to see this building envelope. Okay. Now, building envelope, of course, it goes without saying that in buildings, either most of the buildings in the tropical countries like India, we will be using the cooling. Okay, because temperatures outside are very high, and we want comfortable temperatures within the building. So there is always a cooling. There is a ventilation and cooling. Sometimes we use fans, sometimes we use air conditioner, room air conditioner, sometimes maybe air conditioning system, very large, especially in hotels, hospital, big buildings, commercial office, buildings, government offices. They require a large air conditioning systems to be installed in that. So there we have to ensure that the building envelope is properly sealed so that no heat comes in. Okay, the joints are covered. If it is a heated building, it's the reverse. That means no heat. Heating, heated buildings, especially the cold areas, cold countries, where there is a room heating, they will ensure that there is no heat goes out. Okay, so even there you require various joints. That air should not leak in or out. Okay, infiltrate. So air should not infiltrate in the room, in the building, or exfiltrate. That means heat going out. So joints have to be very proper. Especially the doors and windows. Openings between the wall foundation have to be proper. So civil construction have to ensure that wherever there are no gaps, there are no joints, there is no gaps left out, so there is no leakage. Okay, because if there is a leakage and the cold air uh, inside and hot air comes in, naturally it's going to increase the heating load, and to that extent, air conditioning, electricity consumption is going to increase. So we have to ensure that there are no leakages, there are no gaps. Okay, everywhere, anywhere in the building. Okay, and the design of the envelope also has to be done from the point of view of there are many areas where architects can take care of the design of the building, building envelope. What we mean is the outside. So what are these? First of all, it is the we have to ensure that building is not heated much from outside. Okay, or building is not much exposed. If it is to atmosphere or sun, and vice versa when it is heated up. Okay, so that is in order if that is to be achieved, we have to ensure that the shape of the building, orientation of the building is to be taken into account such that we are able to maintain the proper thermal comfort in the building, whether it is heated or whether it is cooled. So, if the temperature difference is very high, the building has to provide, it has to be properly shaped. Plus, also, there is an insulation required to be provided to insulate the buildings from the outside, atmosphere. For example, the walls, the roof, they do provide insulation. That means outside heat doesn't is restricted. No, not that it doesn't come in, but it is restricted. All roofs, walls, windows, doors, everywhere, we have to ensure that not they don't allow much of heat. Okay, or then don't allow much heat to come in or uh, go out. Okay, so uh, that care is to be taken
Sir, we can
in the
apply reflective paints also, no?
pardon. Yeah, yeah. Reflective paint is one. That is, of course, that is while the painting is done. That means
Yeah.
it is given to the walls mostly. White paint or chemicals they are used as reflective paint. So that is, of course, one that is not a part of the design. We are talking first about what are the points to be covered by the designer. That means by the architect. Okay. So
Okay.
similarly, glazing also, what materials to be used, what shades to be used, doors also, what materials to be used. So they have to design all those, in such a manner that less of heat comes in or goes out. Okay. So there are many provisions required to be done. There are certain shading devices. That means you reduce the heat, sun rays striking the building to the extent possible. So there are shadings. I think all of us, we must be knowing that is called the shaja, when there is a door or when there is window outside, you will always find a projection which is called as the chhajja. That ensure that sun rays don't directly go inside. So some provisions have to be made in the building which will reduce the the rays of radiation or sun rays falling on it. Okay, so that of course will mean that energy uh, energy consumption is going to reduce. Okay, so architects usually they deploy a strategy which is called the solar design. That means they use solar passive design. That means they ensure that the building is designed in such a way that there is either less consumption, there is no consumption or there is less consumption to start with. That means there is adequate lighting, illumination. So they provide more windows, adequate windows, I would say, not more windows, doors. They may provide skylights so that there is light in it. They may provide courtyards, and the glass that will be used also will be proper to ensure that there is proper lighting inside. And so also they will also ensure that there is proper ventilation. That is also very important, because if the ventilation is not good, you have to provide artificial ventilation, or uh, so which requires, of course, the electricity for the ventilation system. So they have to design the envelope in such a manner that it reduces the building. Even the shape of the building and orientation are very important. For example, the buildings which are, you all know that the sun comes up in the east and goes to the west. Okay. So if the building is facing the area which are facing on the east side and the west side, for a long time they are going to be exposed to sun. And then, of course, it means that the sun's radiation, sun's heat will come in. So you design such a building in such a way that the areas exposed to east or west are reduced, and more areas are exposed to north and south. That means the longer sides of the buildings are exposed to north and south, and smaller or the width is exposed to the east and west. That will reduce the energy radiation hitting the building, and so therefore possibility of energy reducing the energy consumption. So this is one thing. Secondly, where to locate the building. We have to properly orient it. Therefore, building. Okay, and especially if there is a road, we have to ensure that the road longer side is parallel to the road, and shorter side is at the perpendicular to the, and so on. So there are some restrictions which are locational. Okay, to that particular area. Okay, because we can't have a building at random. No, uh, uh, and also the shape of the building is also very important. You must have seen that circular shape, building. They for the same volume of building, same occupancy of the building, the surface area is reduced. But sir, everyone cannot design circular building. Of course, circular building, even construction becomes very difficult. But we do see Parliament building, earlier old Parliament building was a circular design. Okay, that we are all seen that. So circular design looks good. Also, it is more amenable to less exposure to sun, or even the cold wind, etc. Everywhere, it gets exposure gets reduced. So that is going to be helpful. But these are the instructions which we, depending on the location, you can't have this as a rule. So architects will design that, but they have to ensure that the shape of the building is properly chosen, and also the location and orientation are also properly chosen. Then, in order to ensure that uh, less energy, less radiation comes through the doors and windows, there is a practice of providing shading devices. There may be two types of shading devices. One is the horizontal, with which we are all used to it, but there can be vertical shading also in certain types of building. So these are also called doors. When it is vertical, it is called doors. When it is called when it is horizontal, they are called the shades. Okay. we have to ensure that there is a good ventilation, cross ventilation, and the roof plays a very important role because sun's rays always hit the roof first. They of course they do hit the walls also, but to a large extent the heat from the sun comes in the building through the roof. So therefore roofs have to be properly designed. You can see in the picture, one is a conventional roof where you can see there a lot of heat coming in. There is some amount of heat also get reflected from the roof, but there is large amount which comes in. Whereas if you want to keep the building atmosphere inside cool, we have to ensure that all heat that falls on the roof gets reflected. Okay, so we have to design the roof in such a manner with the proper types of materials used, and the proper, of course, finish of the surface also. So if you want the cooling effect to be there more or there. Okay, there are two things which we must try to learn before we go to the more about the measure for reducing energy consumption, and that is solar reflectance and acceptance. When the solar rays, you see the figure number 10.3, which describes the solar reflectance, solar absorptance, and thermal emittance. So what are these three? These are the normal terms used more by the architects, but we must understand, if you have to do, energy engineers must understand these terms at least, though they may not be using it much. Okay. You can see the roof of a building and the sun over there. So there are sun's radiations which hit the roof. There are two types of layers you will see. One is the roof, and there is the insulation layer also. One is a dark green and one is a gray. So when the sun's rays hit, so part of that will be reflected. So the amount of reflection, that is the property of the roof to reflect the solar radiation. So that is called the solar reflectance. How much of the rays falling on the roof, they get reflected. The amount of rays now going in, okay, inside the building. So the or absorbed in the roof is called the solar absorptance. Okay, and how much heat will be retained or how much will be emitted, that depends on the property of that roof material uh, to retain, absorb heat and emit. So that becomes the property of the material. Okay. So so these are the three terms which are used by the architects to specify the qualities of roof and qualities of heat rejection or reflectance from the building. I think this is more than enough for us to understand that some heat falling on the roof, partly it goes out through the reflectance. So we should have a surface which will ensure that more heat is reflected, less heat is carried through the roof, and material should be said that not much of that heat will be retained. It will be emitted, it will be thrown back into the atmosphere. So these properties are very important from the consideration of the air conditioning and of course the energy consumption. Now, in addition to this, there are two or three other two major terms which are used by the architects, and we will be also concerned with that. That is, one is the solar heat gain confidence coefficient. Short form normally uses SHGC, solar heat gain confidence first word. Now, what is solar heat gain confidence? Yeah, we have seen that when the sun's rays hit, sun's rays carry both. They carry both light as well as the heat. Sun's rays, solar radiation contains both heat as well as the light. So we are all concerned with that because you want to use that heat from the sun also. You want to use light that we receive from the sun. Okay, as much as possible, because that is going to reduce our requirement of artificial lighting or artificial ventilation and reduce our energy consumption. So these terms become very important to us as well as to the architects for their design. So solar heat gain confidence coefficient is the ratio SHGC is the ratio of solar heat gain that passes through the fenestration. Now, before we go to this, let me explain what is fenestration. Any opening in the roof or in the walls is called fenestration. This is a very popular word used by architects, and energy engineers find it very difficult to understand what is fenestration. No, for us, in simple language, fenestration is an opening through which air and rays, light and air will come in, or it will go. But not all the heat, not all the uh, we want to allow inside. So there is a glazing, that means the glass. So doors, windows, with along with the glass, or there may be skylight, that may roof may be having some skylight, that means the opening which are covered with the grass. So these are called skylight. They allow light but not water or anything, cold air inside. So that how much heat is going in through this fenestration or the opening. So ratio of heat gain, that heat that passes through the fenestration to the total incident on that fenestration area. Okay, are that area of the door, windows, etc. That is a solar heat gain coefficient, and is very important parameter for the design of the building. So architectural design of the building. Okay, so solar gate heat gain includes directly transmitted solar as well as the absorbed also, because windows, etc., the material will also absorb, and which also may be radiated, conducted. So all those considerations have to be done. But it all relates on how much heat is coming in, how much is let out, how much is absorbed, so that we have to know how much is the heat actually transferred to the atmosphere within the building. Okay, for which architects have to design to make it conditions livable. Similarly, second term that is very useful is visible light transmitter. Okay, so visible light transmission means obviously it relates to the light. So the light, you all know that radiation has a part which carries the light. So certain radiations fall in the range of light. They give us the light. So the amount of light or radiation with that light, how much goes in per square, through a particular, fenestration. That means the doors or windows or the roof. Roof means if there are openings in the roof, which allow light to come in. I am sure that you must have seen many buildings, old buildings, which are got on the roof. There is a light. Okay. So their your lighting requirements of artificial lighting reduces. So and of course there are glazing provided, glass provided. So it is the property of the glass that is provided on the openings, that is the doors, windows, or skylights, etc., where which decides how much light is goes in. Okay, in this side. Of course, theoretically, all light must go through, but you can't have a substance which will transmit on entire 100% light. It's not possible. So you have to use materials which will transmit the light as much as possible. So the visible light transmittance, that ratio or coefficient has to be high. Solar heat gain coefficient should be as low as possible, because we want to restrict the heat coming in, because otherwise our air conditioning load will increase, where the visible light transmission, which is the VLT, that has to be as high as possible. So they are conflicting. SHGC is kept to be minimum, and VLT, visible light transmitter, is to be kept maximum by choosing proper materials, okay, of the fenestration, that is the glass. So this picture shows that solar heat gain coefficient and visible transmission. You can see in the picture that solar heat gain coefficient is mentioned as 0.39, which means 39% of the solar heat gain, it is transmitted to the atmosphere within the building, and VLT is 0.71. That means 71% of the visible light can come in. Okay, and as we mentioned, VLT should be high, Hg heat gain coefficient should be as low as possible. So the penetration plays a very important role. The how much area of fenestration you provide, there are certain restrictions over also in that. All building rules, construction design rules by the corporation or by the authorities insist that there should be certain minimum area should be of the wall should be kept, or should allow light to come in. That means the fenestration, there is a restriction, certain minimum area is to be provided. Typically maybe 15% or 30% of the area must be provided by by fenestration, which is covered by light. You can see in figure 10.5, which is a skylight. So those who are not conversant with the skylight uh, can will know from this particular picture. You can see over there. Of course, most of us must be knowing that, I'm sure. Okay, so skylight is, of course, then everywhere it cannot be provided, because if it is slanting roof, usually a very high roof, then only it can be provided. So use of skylights is limited to this. But there are vertical fenestration, that means your windows, doors and windows, they provide the light within the premises, within the within the building. So they also become very important. Certain minimum area is to provided for that. So there are restrictions on the fenestration area that is decided by the corporation. So it shows that for glass doors where glass variation is less than 50%, the fenestration, so fenestration area, there are limitations. Of course, this is the job of architect. We don't have to worry about it. He will be providing that, what is required. Okay. There is another factor which is called the window to wall ratio. That means the openings, especially doors and windows, the area of that, as a ratio of wall area is called the window to wear ratio. So this is a design aspect which is to be taken care of by the architect. We do not, energy engineers, we do not have to worry about it, because this is something which is a part of the building designed by an architect. Okay, so uh, but we have to understand, their terms, because somebody, architects will start saying, or corporations will say whether a window to wall ratio is adequate or not. Okay, we are not so much concerned with it. Also, you know that because there is certain minimum area required to be provided to ensure that light goes in, but of course it has to be covered with a glass. But the type of glass that you use also becomes very important. You might have seen certain buildings where there is glass which is very transparent. Okay, glass which is transparent it looks good, but the point is that all that area is exposed to radiation from sun, and the heat also will go in. You can't have light going in and heat radiation not going in. You can't have that. But of course, there are materials which allow light and which do not allow the radiation. But these are special materials, not the common ones. Okay. So normally, this glass, the type of glass, the material of glass is also very important. That, of course, will be done. The selection will be done by the architect, not by us. So architects have to calculate, window to wall ratio. They have to calculate, that VLT. They have to calculate also the, HSDC, etc. So these energy engineers will not do, but architects have to do it. All architects have to do it. Okay. So they have, and since CBC is also to be taught to architects, this chapter contains all these terms, and all these calculations are mentioned over here, because it's the same chapter which architects also have to go through, and they have to also deployed. They have to use that information to design a particular building. So they explained it in more detail, especially the terms VLT, visible light transmittance, window to wall ratio. These are mentioned over there. Because it is mentioned here, we also have to just go through. So the effective aperture means effective area that is exposed to radiations or sun is the product or is of VLT, visible light transmittance into window to wall ratio. Okay, window to wall ratio means that will decide how much part of the window area is provided and how much VLT means how much light can pass through it. So, example case one is window to wall ratio is 0.4, VLT that allow 0.26% of the visible light inside. So, effective area that is provided for light to come in is 0.4 into 0.26 is equal to 0.104. Okay, and there is a restriction that the glazing must be such provided that the effective aperture must be more than point 0.1. So this is what the architects have to achieve to ensure that the window, glass is selected, glazing. It is also called glazing by the architects. So it must be more than 0.1. Case 2 is considered where window to wall ratio is 0.6, but the VLT, that means the material use is not so good. So it is only 0.15. So the multiplication of these two is 0.09, which means it doesn't comply because if the code says that it must be 0.1, must be the glazing, must be the effective aperture minimum, then that means it is not as per the ECBC. So it will be rejected. So this is what we have to understand. Okay, one more thing which I would like to mention over here, which is not mentioned here. I think I am sure that many of you would have seen the cars. Cars have got windows and there's a glazing. Normally, they insist that windows must have glass to which the police or people should be able to see what is going on inside. Okay, from security reason. But some people provide very dark glass, black glass, and that is not allowed actually. But they do provide. Some car manufacturers provide that. Okay, but that is not correct. So in case of buildings, we can't do that. We can't escape because buildings have to be passed. Their designs have to be passed by the authorities. They will ensure that proper types of glazing is also used. Okay. Now there is another thing which normally architects will talk about. It is the opaque wall. Normally we know that the walls, we always have either the brick walls or we will have the concrete blocks, hollow block. Okay, and they are not transparent. So the walls which doesn't have any opening is called the opaque wall. Okay, so this is one characteristic of some buildings. Especially godowns, uh, you know, uh, can have walls which are opaque walls. Similarly, sound transmission, especially in some areas, especially operation theaters or some patient room and all, sound coming from outside becomes very difficult. And we also find many times, outside sound is coming in and it disturbs us. So sound transmission is also another factor which has to be used by which has to be taken care of by the architects. They will design it, although it has nothing to do much with the energy consumption, but for building performance, of the entire building, acoustics also becomes very important. And it's also vice versa, that in case of a theater or cinema hall, the proper sound, quality of light is required. So there you have to provide the roof, the materials within. They may provide some actually artificial materials also to ensure that proper light, sound conditions are also there. No outside light sound comes in, and also sometimes we don't want light to also sound to also go out. You know, if there is a halla gulla in some areas like a meeting or something like that, it should not go out. So sound transmission has to be also taken care of in especially theaters, hotels, etc. Are concerned. Okay, so I think with this we have covered most of the terms which are which we hear. We may not be using that. Energy people now may not be using many of them, but they have to understand this. Okay, there is one more factor which is often talked by the architects, and which is to be understood to some extent by the energy engineers, is called the U factor. Okay, U factor is, I have always found U factor very difficult to understand. What is U factor? But it is not so as difficult as one might think it to be. The U factor is the quality of the insulation that is provided by the material, for the walls, for the roof, etc., etc. Okay, so different types of building construction, they have got different types of limit. Okay, and also the U value actually defines what is the amount of what is the material should be used, what should be the thickness of the material, etc., etc., to ensure that within the building the required conditions are met. So you can see that opaque wall assembly U factor. So U values are specified for different types of different areas in a building. This is of course you see this information is important to the architects. They will have to ensure that the limits are maintained. So in different climate zones, for example, climate hot and dry, warm, moderate, etc. The hospitals and hotels and call centers installed in this building shall have certain maximum U factor. That means it cannot, it has to ensure that not more than certain amount of heat is passed on. Okay, light is passed on, heat is passed on. And minimum value, that means minimum, it has to ensure that there is certain minimum resistance offered to the heat gain. Okay, heat gain inside or outside. So one is the light, second is the heat. So U factor decides how much is the is the insulation heat transfer coefficient. U factor is the heat transfer coefficient, and R is designate the insulation resistance. Okay, U factor decide how much heat how much of light can be passed on. So these are the limits specified. I will not go through that because we can't remember all these things. And secondly, designers, architects will have to take care of that. Now, U factor, rather not value, U factor is in watts per m square. I think for the examination purposes, certain definitions will be important because you may ask to, optional questions, especially objective questions. They may ask some questions related to certain definitions, certain terms that we have seen. And they may also ask what are the units. So therefore, we have to know that, we have to also answer that. So U value is what is specified in watts per m square. So it is the amount of energy that is transported per square meter. Okay. And R value is the insulation resistance of that particular material. Okay. So R value is also mentioned for a particular atmospheric condition. Okay. For both for hospital, especially the terms are little more rigid. For the normal buildings, some of the quantities you know, there is some relaxation given. That is mentioned over here. Oh, okay, that you can see the values over there. Okay, this is for the opaque walls, and similarly for the roof assembly also it is given. As you can see, more heat radiation falls on the roof, so there are the limits of V value are lower than that for the wall. So these limits are given here. Similarly, for the vertical fenestration, the maximum U factor, the minimum maximum heat gain coefficient, these are all specified. So these are all restrictions within which the buildings have to be designed by the architects, and they have to ensure in the practice that all those are achieved. Okay, so this is what it means. Okay, we have to understand only from the point of examination. Now, as we started with this, that we have to ensure that the energy consumption in the buildings meets the ECBC requirements, and either we can do all this calculation either by prescriptive method. That means for each area there are certain limits provided for energy consumption. We ensure that that particular area, same it may be a hall, it may be it may be hospital theater, it may be rooms, or it may be the balcony, it may be yard. There we will have different limits, or a whole building performance method where everything or building is taken as a unit. uh, Somewhere the values may be more, somewhere values may be lower, but overall the building conforms to certain limit which is specified for energy consumption for unit it's mentioned here. So compliance approach, of course, now there are going to be restrictions, because ECBC is tightened very slowly. Okay. Now, at this point of time, I would like to introduce another concept. I mentioned in the beginning that initially ECBC was, the ECBC 2007. Then it was found that, there was need to make it compulsory. So certain types of buildings slowly, one by one, they were covered under mandatory. That means mandatorily you have to design buildings to ensure that those limits are, these buildings are designed within those limits. But so implementation started for many more types of building. But it was found that the limits which were specified in ECBC 2007, now we are calling it 2007 now, it was ECBC earlier. It's a very, they're very loose. They do not serve the purpose in many cases. So the Energy Conservation Building Code was revised, updated, improved in year 2017. And so therefore it was called a ACBC Code 2017. So which has become more stringent. And subsequently, it was implemented, and again it was found that there is a need to improve this. So they introduced a code called ECBC 2024. Now, ECBC 2024, when they introduced in year 2024, ECBC, they said that by that time we were talking much about the sustainability. So this code, they changed the name to Energy Conservation Sustainability Building Code, ECSBC. So now we will be hearing more about ECSBC and not 2007, not 2017, because those codes are now old. We are going to use both energy conservation people as well as architects. They are going to use ECSBC, ECSBC, Energy Conservation Sustainability Building Code, where the requirements are much, stringent. In ECSBC, there are three types, three levels. One is the normal, so where the limits are lower. One is the special, where the limits are little higher, more stringent, and one is super ECBC. So super ESCBC, where the requirements are very, very stringent. Okay. Now there are certain requirements where you have to ensure design which will abide by ECSBC super. So we are not going to study ECSBC 2017 because this book we are only talking about 2015. Okay, this is easy. This book was published in 2015. So whatever we are going to questions we are going to be asked to us is pertaining to ECBC or ECBC 2007 only, not ECSB. But you should understand, you should know that we have progressed much more than that. Okay. Now let's come back to ECBC. Now, what are the ECBC guidelines for heating, ventilation, and air conditioning. We have seen for the envelope, the walls, buildings, roofs, ventilation, glazing, etc., which is the major part of the building, more related to the architectural part of the building. Okay, but control there is required because energy consumption is very much depend on the type of construction. Architects have to know it, and also the energy engineer has to provide the backup. They have to teach architects that this is what we need for reducing energy consumption. But now let's go to the another part of it. The building is never only the envelope. Okay, the building that we live in, either in our house or we go to the school, we go to college, we go to hospital, we go to the hotel, or public building, and so on. There are certain activities which are carried out. Okay, and depending on the activity that is carried out, you have to provide various types of utility system. For example, electricity is required for lighting everywhere. All types of building will require lighting. So electricity is a must. Electricity requires water supply. Sorry, buildings require water supply. What water needs to be distributed at various places. So you need there is a water circulating system is required. Then some of the buildings are air conditioned, some are may not be air conditioned. They require only fans. So you have to provide that ventilation system, or you have to provide the air conditioning system. Okay, depending on what is the climate zone, uh, and buildings have to be designed accordingly. Some buildings which are in the cold region, they will have to be designed as a heated building. So the design aspects of that is different, and the energy consumption cost aspects of these three are different. So there are guidelines provided for both heating system, ventilation system, and air conditioning system, which are a part of the building. Actually, the entire air energy consumption takes place after the building is constructed is because of the various utilities. It may be either the lighting, it may be heating, when, you know, heating, ventilation, air conditioning. It may be you have got lifts, we have got escalators. It may be using that. So various utilities system which have been provided in a building which utilize energy. There are guidelines for each of them, or the utility system. So utility system, actually, energy engineers are more conversant with the how to save energy in the utility system. So they come in picture more for the utility part of it. That means how to save energy part of it, not the architect. So architects only is more or less limited to building design, architectural aspect, the ventilation aspect, etc., heat going, etc., etc. But air conditioning, ventilation, and other utility system, energy engineers will be more involved. So we have to now understand more about all these systems, where the energy consumption takes place and how to reduce it. Now the principles of this are not different from what we have studied for, as a part of our book 1, book 2, and book 3. Okay. Uh, but anyway, for the building, there are some specific requirements. So we are going to see what are the specific requirements of which are mentioned in the ECBC. What are the limits mentioned at the for the utility system in the building? So let us go one by one. Let us see that. The first system is the HVAC, or heating, ventilation, and air conditioning, where the equipment efficiency becomes very important. That means the HVAC system must be efficient. In HVAC system, the chiller is the highest energy consuming component of that. So chillers have to be very, very efficient. So there are limit mentioned about the efficiency of the chillers by specifying some limits for them. Now, there are two standards which apply to utilities. One of them is the Bureau of Indian Standard, BIS. They also lay down certain limitations on the utility system performance pump, or the utility cooling system, heating system. There are certain provisions mentioned in the Bureau of Indian Standard. So there are BIS codes which the building has to comply with. Second code that also comes into picture, especially in the HVAC, is the ASHRAE or ISHRAE. Now, ASHRAE and ISHRAE specify a certain amount of limits for air conditioning system, chillers and all. So efficiency of the chillers, etc. They are specified by ASHRAE. So the building design has to ensure, a building utility system has to ensure that they have to comply both with ASHRAE as well as BIS code. Okay, and energy engineers will have to ensure that the utilities designed by the architect comply with ECBC requirement. That will have to ensure, especially if the audit is carried out, whether it is ECBC building is energy compliant or not. All these points become very important, and ECBC auditors will have to ensure whether each of the limit is not exceeded. Okay, so knowledge of this becomes very, very important to us. So in case of AC system, there are certain controls which we could need to provide it. That means there is a to be automatic on and off. Now, where to provide the controls? What should the controls? What should the temperature limit? It will be specified in the ECBC. But basically, if the HVAC the load is more than 28 kilowatt, there are restrictions which are mentioned over in the ECBC document, which have to be followed. So there are certain controls which require to be provided. Air conditioned area, you have to have certain controls there may be time control. That means for certain hours the air conditioning equipment may be on, certain period it may be off to ensure certain temperature. If it is continuously on, the consumption is going to be more. But if you want to reduce it, it should not happen that temperatures shoot beyond the limit. So there is controls have to be provided so that temperature are within certain temperature limits. So that controls are essential for that. Similarly, the air conditioning system, the cold, either it is the cold, chilled water which is circulated, or the cold air that is circulated, especially in theaters, etc. There are many times it is air cooled theater, or chilled water is used for air conditioning plants. Okay, so the distribution system has to be accordingly designed and ensure that the limits are what is specified are they abide by it. Okay, so ECBC has made certain provisions in the code. They have to ensure that the architects take care of those in the design itself. Okay, and of course it goes without saying that the ceiling, the duct or the pipes or the gases of the distribution system, they are covered. They are also insulated. Especially if it is chilled water uh, going through the pipes to the air handling units in the air conditioned area. The pipes cannot be left open because otherwise the heat, it will gain the heat. So you have to again keep it, make it more cold. So your energy consumption is bound to increase. So that there is a restriction on that. So they provide insulation. So it is a heat insulation which is provided, on the chilled water piping or ducts. There may be ducts in some cases. There may not be pipes for air. Certain theaters, they provide air ducts for carrying the cool air inside the premises. So they need to be insulated. So ducts and pipelines need to be insulated, and of course one has to ensure that there is no leakage. No, because ducts and piping, there are going to be joints. You cannot have in one pipe, one leg. So your joints will be there. So you have to ensure that joints are not taking proper gasketing are done. There are no leakages, proper materials are used, insulation is provided so that no heat is either lost or no heat is gained. There are certain systems which are more sophisticated, like air system balancing. That is a part of the AC system, HVAC. I don't think we should talk about it more here because that's a part of the air conditioning design. and people will take care of it. Okay. Energy engineers have got very almost no role to play in system air balancing, etc. Okay. So we'll skip this. Similarly, hydronic system, that means the pressure equalization, which means that in a building, water must flow equally to all the floors, or air must flow equally to all the areas. So there are certain systems which are balancing system. So that is a part of the again design of the system, not so much with the energy part of it. Okay. So this is mentioned more detail over there. Those who are going to be involved in the design or in the field, they can study on that. There are certain there is certain provision of what is called the economizer. You know that boilers, there are economizers. That means you are using whatever the waste heat going out to the flue gases, that they are recirculating and using it for heating water. That's an economizer. Similarly, in the building, there are certain economizers, especially you know uh, in certain areas you need to fix it up. That means the cold air going out, that must be recirculated and so on and things. So economizers are also a part of the building. Okay. So this is as far as the HVAC system is concerned. Okay. Restrictions on the chiller efficiency, restrictions on the leakage controls provided for the temperature control, etc. Now there is another system which is very common in hotels, hospitals, uh, large public building is the service hot water. Hotels, hospitals, etc. They have to provide hot water to the occupants, to the patients. You see. So there are certain restrictions that nowadays, if there is a hot water system installed, you normally heat it either by electricity or by using certain fuels. Now, in order to reduce the consumption of fuels or electricity, they are insisting that the solar water heating becomes a part of the heating system. That means water that is provided in hotels, hospitals, commercial building, part of that must be using the water heating. So restriction today is 20% of the hot water heating should be done by solar water heating. Okay. So this limit may change over a period of time. So that is to reduce that remaining 80% you have to use energy, either heat source or maybe electricity. So this system, that 80% component, which is called the supplementary heating system, that means artificially we have to heat water. So there are restrictions on the performance of those particular system. So we have to ensure that there is a maximum heat recovery in those particular system. So in case of gas-fired heaters, you have to ensure that proper gas is available. Instead of in case of electrical heating, that last choice, because gas heating is much cheaper, and nobody uses, of course, oil heating. Gas heating is very common in most of the Western countries. Large part of Europe, Russia, Canada, USA, Australia. They are all using gas for heating. So heating becomes very important. Though. So there, you have to ensure that proper gas is used, and there are restrictions on that. Electricity will be used only where you don't have any other source. You use electricity, but electrical means it's more energy you are consuming. I think you all know that in case of even your resident, if there are many gas geysers which are used, which consume less, expenditure also less, consumption is also less. Electric heaters will consume much more, expenses also will much more. And in all this water heating system, because again, heated water flows through a distribution system, it's taken to various places within the premises of the building. So piping has to be insulated. If there is the duct, it is to be insulated by using proper material. Okay. In case of steam, where steam is fed into various areas in a building, that becomes a part of the building, in some cases. And there the heat traps becomes very, very important. In case of hot water, you have to provide some heat traps so that if there is a impurity, it has to be thrown out. So swimming pools, etc., there are some restrictions on that. Okay, so this is regarding the heating system. Hope you understood. You understood?
Yes, sir. Yes.
Okay, now let us go to the another very important part where uh, energy engineers, electrical engineers play a more important role. Okay, architects also do play a role because they have to specify certain amount of certain amount of illumination minimum that is specified as per the standards. So they have to provide certain minimum illumination intensity within the premises, uh, depending on the use. Of course, you also know that everywhere the illumination levels are going up, because people need more light. They want to have more better atmosphere, especially where they're learning, where they're reading, they're doing certain work. So, science has also told us that better light, it improves also the efficiency of working of people. So, more tendency to use more lighting, but more lighting means more lamps, more energy consumption. Okay. Whereas on one hand, we are saying that energy consumption must be reduced, but on the other hand, we want to increase the illumination level, we want to increase the more comfort, visual effect, etc., etc. So these are conflicting requirements. So there has to be a compromise done by the energy engineers and architects together. Okay. So and so therefore the design of lighting system, or I would put it, say the illumination system becomes very, very important from the point of view of energy consumption reduction. So for improving energy efficiency in lighting, there are many steps which can be taken. One is, of course, the types of lamps you choose. There are all new developments which are taking place. You would have seen that every 3 or 4 years, a new type of lamps have come. In last century, last 2 decades of earlier century and first 2 decades of this century, large number of lamps have been developed which are more energy efficient. In fact, all the lighting design, the lamp design, innovation is to reduce the energy consumption or improve the luminous efficacy. That means luminous efficiency. That means you provide less input and get more light output. That is the trend for last many years, and that is continuing. So we have to worry about various areas where lights are provided, illumination is provided, and these are one of the interior spaces of the building. Okay, and that's most important because uh, depending on the activity that is carried out inside the building, there is certain requirement of illumination, certain requirement of lighting, the type of lighting, color of lighting, intensity of lighting. You don't need shades, you don't need glare. So many requirements are there. But finally, you have to also ensure that energy consumption also gets reduced because it's a large component of the total energy consumption in the building. So interior spaces becomes very important for illumination point of view. Exterior building surface, for example, facades are there, illuminated roofs will be there, street lighting will be there, some architecture features where you want to, throw light on the surface, etc. So these are some special requirements you have to use proper types of light. Okay, that illumination level may not be important over there. Of course, in street lighting, it is important. Yard lighting, it is important. Suppose you have a cricket match, you have to have proper lighting, illumination design. Otherwise, if the batsman doesn't see a ball or the fielder doesn't see a ball, he can't catch. Or if the batsman doesn't see a ball, he will be bowled. So, for the sports also, it becomes very important that certain illumination levels are maintained. But even there, for the sport complex also, we have to reduce energy consumption. So, we have to use efficient lamps. Okay, and distribution. How do you distribute the light? It also becomes important so that there's no glare, there's no dark path. Okay, so all these requirements are there. So it becomes very, very important that uh, energy engineers also must understand, just as architects also need to understand the requirements of illumination. So illumination is one, or lighting is one, where both inputs are very, very essential. Then you have got the external building grounds. That's what we explained just now. Okay. And so therefore it is important to understand many facets of lighting. So lighting, you have to have a lighting control. That means you have to have certain minimum illumination level. We have to have, first of all, on and off lighting. We know that in the room we have got switches. We make the switch on and the light is on, and we are supposed to switch off when we are going out of the room. Okay, and that's everywhere. If it's a hall, there are a number of lights which are controlled by a switch. In house, one light, one switch per light, but that's not possible in a hall or big area. So where it will be multiple lights are controlled by a switch. Now, in some cases, people leave it just like that, especially public area. Once the show is over, activity is over, office is over, people go out, they don't switch off. So there has to be some control provided that automatically things will be, lighting system will be switched off, so that electrical supply will be switched off. So lighting control becomes very important depending on the activity in a particular place. Okay, in the residence, it's not that much, but in case of large building, public buildings, lighting control become very important. So there are provisions in the ECBC that what types of lighting control should be provided is mentioned over here. Okay, we'll have to study that over there. In some cases, in certain areas, especially meeting room, director's room, board room, where when the people leave, lights will be on. So normally there is a method that occupancy sensor will be used. That means if there is no one in that particular room, it will be sensed by this occupancy sensor and it will switch off the supply to that lighting system. So these types of controls are there, are going to be there. In some cases, you know that you go to the picture hall. Initially, when you enter, there has to be proper light so that people can go in and sit in the proper places. After a certain time, the illumination level will drop to some extent. And when the show is on, only the stage lights will be on and other lights will go on. So lighting control becomes extremely important in most of the areas, okay, depending on the activity. So this becomes very important. But at the same time, energy consumption cannot be ignored. And so certain terms which there are certain limits on the energy consumption, in the lighting. So that is what we have to study, we have to understand. So one term that is used always is the lighting power density, LPD. So lighting power density is nothing but the amount of power that is used, to provide illumination. You know, so the wattage that is provided, for certain illumination, you require certain lamp. They will have certain wattage. The total of all the wattage of the lamps is the total wattage of lighting system. And the area, if so yeah, they calculate a ratio of the power density per square, per unit area, and there are restrictions on that. Depending on the activity, there are different limits are specified. If it is library, it's a different limit. If it's a residence, it's different. If it is a lobby, it is different. Okay, so different areas will have different to be specified for ensuring that there is uh, energy consumption is limited to a certain value, although keeping in mind that other provisions of requirement must be of course maintained. That means no comfort is taken out. No, if reading comfort required, you have to provide illumination. Yeah, if you have to do some precision work, that much illumination will have to be provided. But how to do it? That is the job of lighting engineers, because if it is very precision job, you don't require, generally you have to be designed also for that high illumination intensity. So that design will be done properly. But all the same, you have to reduce the energy consumption. Now there are two methods, in which energy consumption is controlled in a building. One is the building area method, and one is space function method. Okay. So what are these? And there are different time limits specified for this. So what is the building area method? So you determine for a particular area, you know what is the total lighting load, and divided by the area. The factor that you get is called the lighting power density. Okay, that means the power density for a particular area. It is called the LPD, lighting power density. You know, so for example, there is an example given over here for the interior lighting. That means within the premises of the building. Obviously, it is going to move more. Now, the example that is mentioned over here is a hotel has got 4 floors where each area is 1000 m square. LPD is 10.8. Now, what is LPD? LPD is the lighting power density limit, design limit. Okay, that means it is allowed. That means you can't exceed this power beyond a particular value. Total amount of wattage divided by the area, the value that you get cannot exceed a particular value. That is called as the LPD, lighting power density. That is the limit given over there. So for this particular building, the lighting power density in that particular hotel room is given at 10.8 watts per square meter. So therefore, the interior lighting power around, that means the amount of lamps that the wattage of the lamp that you provide is 1000 is the area square meter. LPD is 10.8. So 10.8 multiplied by 1000, if we multiply, and the 4 floors. So this that is the 4 lakh 32, sorry, 43,200 watt. That means the total lighting wattage cannot exceed 43.2. Okay, because limit on LPD is 10.8. So for each area, that LPD will be specified for different area. Kitchen, it will be different. Lobby, it will be different. Study room, it will be different. Library, it will be different. Common room, it will be different, and so on and so forth. So these are all specified in the uh, ECBC, and depending on what is that area, what is the building area, what is the name of that building area. Yeah, there is a limit over there. Okay, so this is one. Second is the space function method. So what is space function method? Is the activity that you carry out. Okay, so you got there is a limit specified for the activity. For kitchen it will be different, for library it will be different. That means the LPD is mentioned differently for different, different types of activities which take place. One is a general lighting power density, one is a specific for particular area. So if an office, the example given here is an ultra office has got 400 m square as the area for office. The LPD specified is office area, it is specified at 11.8. So how much wattage can be allowed is 400 into 11.8, which means 4,720. That is the only total load that is allowable. You cannot design a system where the wattage will exceed 4.7. That is what it is. So either you can follow any of the methods, building area. That means you have different, you have got a common LPD for an entire building space, or you have got specific LPD used for design of lighting system for a particular area. So illumination engineers and also energy engineers will decide that. Architects also comes into picture because he has to provide the lighting of a proper quality, proper light, color, etc., etc. So becomes very important. Then, especially if you go to theaters, cinema halls, there are exit signs they have to provide, and that also will consume certain amount of energy. So there are some limits specified for that exit lighting also. So also for many, almost all buildings, you will have exterior lighting. That means outside lighting, yard lighting, court lighting, street lighting. So there are limits specified for those also. That means how much is the LPD, lighting power density for those areas, exterior lighting that is mentioned over here. So this is as regard the the lighting, which becomes a very important part of the design of the buildings. In fact, next to the envelope architecture, lighting is another important thing where the energy consumption also plays a very important part because lighting loads are going up everywhere. So energy engineers and architects, they have to work together to ensure that lighting power densities limits are not exceeded or within that. So there are new development in the lighting taking place. So you have to find out which are the new uh, efficient lamps. So energy efficiency of the lamps becomes extremely important over there. And color, of course, some people want is white color, some people want is yellow color, some people want is daylight color, some people want blue color, etc., etc. So for this, there are different limits which have to be in the ECBC, which we need to abide by. So this is regarding the lighting. Hope you understood. Is it clear?
Yes, sir.
Okay. So, but lighting is an important aspect. Okay. Please remember that as far as ECBC is concerned. The next is, of course, electrical power because electricity is required for each and every building. So, so you have to have an electrical system which is also more efficient. Okay. You can't have electrical system which is not efficient. For example, there are transformers, there are motors, there's a power factor limit, distribution losses may be there. So there is restriction on all these things, especially distribution transformer, energy, they are specifying limits on efficiency value on the 50% and 100% load. Okay. So transformers limits mentioned are what should be the efficiency? There should be certain minimum efficiency at full load and 50% of the load because many times we find that transformers are never loaded fully. So both the efficiency values are specified. You have to ensure that transformers are chosen with minimum those efficiency level. Okay. Uh, uh, so, so that is one restriction. Second restriction is the power system is on the motors. So you all know, I think we have all studied about that energy efficient motors are the that's what we are following these days. And building becomes very important because buildings there are certain systems which are often you go to hospital or you go to hotel, especially hospital, you find that lifts, escalator, they are always in use. So there are certain controls on the lift usage. There are certain controls on the you know kilowatt rating of the motors. There are also restrictions on the energy efficiency of the motor. So energy efficient motors are being used over there where the usages are more. This code specified that what should be the efficiency level, for the motors and also transformer, for particular application. I will not go through that. There are certain limitations where if the usage is more because the lifts in hotel uh, will be used much more or public space will much more than lifts in other places. So restrictions are different for different use and number of hours of usage. They decide on that. There are certain standards specified for motors. The standard is 12615 energy efficient motors that is to be used. Okay. Then there are restrictions also on the electrical power distribution system. Okay. And the restriction is that what type of metering you should do. Because finally, unless you use the proper metering, you will not know what is the consumption, what is the, what is the demand and so on. And you need to control both. You need to also control the energy expenses. So we need to know what is the demand, what is the kilowatt hour consumption. So there are restrictions on the usage or installation of the certain measuring equipment, measuring instrument. So, for example, if the electrical supply is exceeding 100 amps, now I don't understand why they are saying 100 amps because we always say so much of kW load is there. But anyway, ECBC does specify that, so we'll have to avoid by that. So the electricity supply, the current that goes is more than 100 amperes if it's a three-phase connection. the power factor has to be more than 0.95. Okay, so we have to ensure that power factor is between 0.95 lakh and unity. You can't have below 0.95 lakh. That is one restriction. Okay, on large system where the current carrying capacity is more than 100 amperes. Okay. Similarly, if the service requirement, the transformer, the capacity of the system more than 1000 kVA, it will have kVA meter installed in it, it will have energy meter installed in it, and it will have power factor meter installed in it. To restrict the power factor, ensure it is more than 0.5, energy consumption, kWh meter, and kVA, that demand is not there, because you are charged for large system on the basis of demand also. So this it becomes very important. And there is another restriction, is called as a total harmonic distortion, because the waveform of the electrical power distribution system may not be perfectly sinusoidal as we want it to be. Most of the times it is distorted because of the loads. We are the culprit. The user is a culprit. We use linear loads more, UPS more, then distortion is going to be more, harmonics are going to be more. So there is a restriction on the total harmonic distortion in the electrical supply. And so you have to provide a meter for that. If so, this is for if the system is large, of large electrical capacity. If the system is between 65 kVA and 1000 kVA, that means a small, medium-sized system, they must have, kilowatt kW meters installed in it, energy meters. So you don't require kVA meter there, kilowatt meters, energy meters, and total power factor. Because most of the places, you are charged on the basis of demand in kW. Okay. But now there is a change which is taking place, that you are also charged on the basis of kVA. You may be charged on the basis of kVAR. So these requirements are bound to change over a period of time. These are what is mentioned in ECBC 2007. Okay, or old ECBC. These are the limits. So if the service is capacity is 1000, below 1000 to 665 to 1000, you have to provide demand meter, kW, energy meter, kWh, and power factor meter. And if the system is very small, where the service, the current carried is less than 65, the capacity is less than 65 kVA, you have to only measure the kWh, because you will be normally, such installation which are on the basis of only kWh. Okay, so these are the limitations of the power system. So these are, and then the pumping system, water pumping system is another very important area in buildings, especially hotels, you know, uh, hospitals and public buildings. So we have to ensure that the pumps are selected such that they run to the capacity of 50% at least. So you have to choose a proper pump capacity. You may choose more number of pumps, operate less number of pumps, choose more number of pumps as per the requirement, especially water supply systems, sewage water supply system, uh, uh, pure water supply system. This becomes very important, and all this we have studied as a part of the pump system. So we are not going to repeat all this here. Okay, but one more very specific requirements of the building is UPS. That means the uninterruptible power supply. So everywhere now the need is, especially we are using computers, we are using some sophisticated computer-based control. So the requirement is that all these equipment must be provided with uninterruptible power supply. So usual practice is that very critical installation, they have their own separate power supply, or they use what is called as the uninterruptible power supply, UPS. I think we are all conversant with UPS, because I'm sure we have experienced so many times our laptop, our supply goes in our building, then we become helpless. We can't do anything. Okay. Of course, you may provide standbys, but they limit to which standby is provided. So UPS is provided. So supply goes and comes back within a few seconds, few minutes. You can still carry on with your operation. So it is called the UPS. Now this UPS, also there is consumes again energy, because after all, what is UPS? In UPS, as the picture shows here, there are two types of systems over here. One is the online UPS, one is the offline UPS. Offline UPS means when there is no supply, the system becomes on. Okay. Online UPS is that you while your supply is on, still you keep that UPS on, so that because you don't want any, even in the smallest of the breakage, you don't want it. So there both provisions are made in the buildings. Okay, so UPS is basically for a building. And what is UPS? You all know that, but I would just like to make it very clear, because there are some misnomers, especially many people say, I have installed inverter. Okay, you don't install inverter. You install basically what is a UPS system. So what is a UPS system? In UPS system, the we get AC supply, three-phase AC supply, 50-second supply. Okay. In a UPS, you provide a storage. Okay. That storage can be used when the supply goes or supply failure there. You use that storage. Again, you have to revert back to AC, because all your equipments are operating on AC. So you store in a battery. Battery is a DC device. Okay. So what you need to do is, in order to store electrical power in a battery, you have to convert it. Converting AC into DC is a conversion. So you need a converter. Okay. And when you want to use that storage to supply your loads, AC loads, you have to invert it. So what you need use is the inverter. So UPS system has got two components. One is a converter, and a second is a inverter. Both are essential components of it. And battery is a storage device. Now, depending on the requirement of your storage, you select a proper battery. But battery means there is a loss, there is a consumption in the battery itself. Okay, there is a heat, it is distributed through heat. So you have to use efficient system even there, and so there are limits mentioned for the UPS system also, which are mentioned over here. I will not go through the further details of that, because they are different for different building types of building. Okay. Then, so this is regarding the UPS system. Then another very important element in the buildings is the escalators and elevators. So again, all buildings nowadays, you have got tall buildings, even residential buildings. I know I have stayed in three-story building. We had no lift, no escalator. But nowadays you can't have. Earlier rule was that up to 5 floors you did not need a lift. So we have stayed in that. But now all buildings are maybe 11 floors, 9 floors, 24, 24, and going to, I don't know, I have gone to Empire State Building, which was, 72 floors was the first hall, 108-story building. Now in Dubai, you have got, which are, I think, more than 200 storage. So all this will have escalators, very fast escalator, very powerful escalator. So lifts with tremendous amount of wattage will be there. Similarly, conveyor systems will be there. Sometimes especially airport and all, you have got conveyor system. We use lot of energy over there. So elevators, escalators, conveyors, they use energy, and so there are limits specified for limiting the energy consumption over there. So here you have to choose proper wattage, proper of the system. Losses in the system, elevator and other systems have to be also controlled. So depending on the type of equipment used, you have to there are certain limits specified to reduce the energy consumption. Okay, so this was the last component of the building. Now let's go through into 2 or 3 minutes about the building energy management system. Now many buildings, they have got all of us stayed in hotels, and we have seen that where the rooms are air conditioned. A person lives, we leave out, we go out. Normally we never bother to switch off the lights or switch off the air conditioning. So that part has to be taken care of by the owners, who are operating the hotel or the other building. Now, so they all buildings now, big building, they control the temperatures within the particular areas. If you want more, less temperature, more temperature, you can control. There are controls provided in the building, in the rooms itself, but there are some central controls which are installed, to switch off, switch on in the rooms which are not under use, areas which are not under use, or areas where there are less density of people is there, and so on and so forth. So building management systems are used everywhere in the hotels, hospitals, etc. And now energy consumption being very important, energy that is also included as a part of the system. So these systems are called building energy management system. Now, the building management system ensures that the energy consumption for heat, HVAC, energy consumption for lighting is is minimized, controlled and minimized. So wherever there is no usage, less usage, you ensure that these controls are employed to reduce the overall energy consumption. So these are becoming very important these days. And there is the last thing that we need to know is the star rating of the building. Just as we have studied the star rating of the equipment. Similarly, buildings also have star rating. In fact, ECBC specifies 5 rating, 1 star, 2 star, 3 star, 4 star, 5 star. 1 star is the least efficient or more energy consuming. 5 star is the most efficient type of building. So depending on the parameter that is the criteria is the energy consumption performance, EPI, energy performance index. Now that is the amount of watt hour, kilowatt hours per square area of that particular device, EPI. That is called the energy performance index. And there are certain limits provided for level 1, level 2, level 3, and buildings are rated according to that. Okay. And nowadays there are green buildings which also require less consumption. So they also ensure that energy consumption is reduced over there. So EPI is one of the parameters. There is another parameter which is annual hourly energy performance index, which is AAHEPI. So energy performance index is kJWH per square meter per year. Okay, so within a year, annual hourly energy performance index is AAHEPC. That is also criteria in certain cases where the unit is watt hour, kWH or watt hour per square meter per hour, not per year. Okay, so these two are different. Both are calculated as a parameter. Okay, so there are many areas in the buildings. We'll just run through in a minute. Air conditioning area is one where energy consumption is to be reduced. We have to control temperature. We have to control humidity. We have to control chilled water temperature. We have to control cooling tower there, its operation, ventilation, air handling units, fans, efficient fans, lighting system. We discuss more. It's enough. As far as possible, use more of daylight, use less of artificial lighting. That means use less energy for lighting. Okay, so there are many controls for it, switch on, switch off, etc., etc. And their design itself is certain provisions have to be made because switches, etc., cannot be controls cannot be provided later on. So these are the things which are involved. The type of fixture, type of lamps, also the room index, room surface, room color, all these things become extremely important. So all these things go into the energy efficiency improvement of the building or energy consumption reduction. And there are limits provided in the energy conservation building code for different areas, for different systems, which energy engineers and architects both have to understand what together produce that. So we have covered the chapter. Let's not, it's a very easy chapter that way, because once we study this, then implement, understanding becomes much easier. Okay. In one lecture, it may not be clear, but it's not very difficult to understand. Am I right?
Yes, sir.
This is perhaps one of the simplest areas where you can quickly grasp. Some terms we may have to go through again and again because, especially building related terms, we may not be conversant, but we have to learn.
Yes.
Okay, so now last thing we will go through is the question and answer. Is the So you have to answer the questions. Question is EC Act covers building having connected load of 500 kilowatt, 500 kVA, 100 kilowatt, and all HT.
100 kilowatt. See,
100 kilowatt, right? Yeah,
100.
you are, yeah, right. I mean, revised 2010 Electricity Act is 100 kilowatt or 120 kVA. Okay. Second question is LPD in ECBC refers to.
Lighting power
Uh,
density.
Correct. That is power density. Very good. Quick answer. Third is Energy Performance Index (EPI) is total building annual energy consumption for built-up area or carpet area or total building energy consumption or HVAC or none. Now this may not be all that easy. A,
I think, yeah, it is yes, sir.
you will say A or B, but you have to go only one answer. Yes, I am expecting answer. A or B?
Yes, sir. It's
A.
B. B.
B, because we are concerned with what is inside in the building, and that is the carpet area. Okay. Now question number 4 is which of the following is not a climate zone?
answer is, sir, built up area for A, yeah, B. Answer.
Okay, so it is controversial. Perhaps they may give yes to both. Okay, because uh, I mean you may not make that final distinction. Okay,
Yes,
so
but sir, actually in external area also there is a compliance for the lighting. So I think built up area will be more appropriate.
well, there can be again two opinions on that.
Okay, okay.
So let us leave it at that. So, uh, but I would say that it is a carpet area because it's a used area. Okay, built up area is not you. You are not bothered about the outside what happens. Okay, now, built up area includes walls. Built up area includes other areas. How we are concerned with that. So anyway, this can be controversial. But let's go to the next session. Which of the following is not a climate zone as per ECBC? It's easy answer A, B, C, or D. Hot, dry, hot, humid, cold, or cold, humid. Yes, somebody has to answer.
Cold, cold, humid.
Yeah, that is not mentioned. It is. We started with this. Yeah, we started the chapter with that. What are the climate? And there is no mention of cold, humid. So uh, not covered in ECBC. The next one, a cool roof is it absorbs heat, reflects heat, transmits heat, or conducts heat.
Absorbs it.
How can it be cool? A cool roof.
Transmits it. Reflects it, sir.
The answer is reflect. It reflects. We have seen
That's
that
why it will be
picture.
cold.
Radiation is coming on the roof and everything going up. That means there's no retention. So that is the coolest roof. Okay. We have seen that
Okay.
picture actually. Okay. That figure we have seen. Next one is HSGC. SHGC is what? Solar heat gain coefficient, solar hot water gain coefficient, or standard heat gain, or standard hot glass.
A.
Solar heat gain
Solar heat.
coefficient, sir.
A. I think everyone will write the answer A. Correct. Next one is which one is not a fenestration? Okay. That's why, some questions will be related to the architecture. So we have to understand, therefore, the terms. So fenestration is windows or skylights or ventilators or walls.
Valves, sir, valves.
The answer is walls because, windows light has to be allowed. Skylights is meant for that. Ventilators also for that. Okay. So walls is the correct answer. The next one is the ratio of daylight passing through the glazing to the light passing through the perfect transmittive glazing. So perfect glass and the glass that is provided, tinted glass or whatever. What is it? What is that ratio called?
Glazing coefficient.
Visual light transmitters.
Yeah, you see, we have to find out how much light passing through that glazing, how much light is passing. Okay, so it is not the glazing coefficient, it is how much amount of light that passes, so visible light transmitter. Okay, how much light is allowed inside the premises. VLT is the answer. Next, last ninth one, the unit of AAHEPI is A or B or C or D.
D.
Yes,
WH square meter.
yeah,
WH square meter per hour.
yeah,
C.
D.
C.
Uh, uh,
C.
or
C. It is
C.
given in the book C.
Oh, so it is per hour. So AHPPI has to have hour unit. So only B and C. And the unit A is wattage. So consumption, watt hour. C is the correct answer.
C.
At number 10, UPS is conversion factor of AC to DC is called what? Converter, charger,
Converter.
battery,
A converter.
converter. I think all of us know that. Okay. So with these objective questions, again important. So we have to understand a little bit of other coefficient factors, etc. Now there are some short questions. There are long questions. I will not go through that. There could be some. Uh, there will be one more lecture. Where numericals will be there. That will be on buildings and commercial establishment, which will be given by an architect. So it will be better that he tells you, from architectural perspective, so that you get both energy perspective and architecture. So he'll be taking that up. Okay. Sorry, I exceeded time by 5 minutes because we started, a bit late. I think I will stop sharing. First, I will stop sharing. Okay. I will stop recording now.